Google I/O is just around the corner.
And we're really excited to show you what we've been cooking up.
For the first time, in addition to our live streams, we are rolling out over 100 I/O Bytes.
Short videos to help developers like you dive in.
And experience I/O anytime, anywhere.
We're delivering more content.
And making it easier than ever to design,
Develop.
And distribute.
And making it even more accessible.
And it's all for you.
It's just for you.
It's all just for you.
So let's say that you got some awesome Android game with hundreds of thousands of downloads, but it seems like you can't break that million user mark. The reason? Users are unhappy with your game's performance. You see, users notice bad performance before any other feature in your game, before your item stats or your UI interfaces, or how in level 3 one of your characters is actually speaking Klingon. And guess what? Users unhappy with performance give bad reviews at a higher percentage than any other problem in your game. So you want to break the million user mark? You're going to have to fix the perf problems in your game. And for modern Android games, that starts with understanding that there exists a delicate dance, a tango, if you will, of interaction between the CPU and GPU in your game that can have a drastic impact on your performance. And the dance works a little something like this. Modern graphics APIs don't allow the CPU to talk directly to the GPU hardware. Instead, it uses an intermediate process known as a graphics driver to handle communication between the two. Drawing calls from the CPU are cached by the driver in a message queue, and when the GPU hardware is ready for work, it will start consuming commands from the same resource and begin executing on them. The existence of the message queue process in the driver means that the CPU can be pushing messages into the driver at a different rate than the GPU is reading from it. And as such, your GPU can be consuming, processing, and drawing data that's around 1 to 2 frames behind the CPU. Now, while alarming, don't worry, this is actually really typical of modern hardware architectures. But with this in mind, understand that hitting 60 frames a second in your game requires both your CPU frame and your GPU frame to both complete their work in around 16 milliseconds. When either of these two systems starts to go out of sync and take longer than that, bad things happen to your frame rate. For example, what if your GPU has more work to do than your CPU? This means that your CPU is going to be submitting frames into the driver at a faster frequency than the GPU is actually going to be consuming them. Eventually, the driver queue is going to get filled, and anytime the CPU wants to submit a driver call, it'll have to block, wait for the GPU to clear up some commands in order to free up space, at which point the CPU can then carry on and submit its new commands. On the other hand, if you're CPU bound, then you're inserting bubbles into your GPU pipeline. Every time the CPU submits a frame, the GPU will consume it immediately, process it, and sit around waiting for the next frame where it can do work again. The straightforward way to fix this is to simply do less work on the CPU. But in this case, it may be that the GPU simply doesn't have enough work to do, and the correct action is actually to give it more work in order to fully maximize the GPU throughput. There's a great opportunity to put like 200 extra zombies on the screen for your designers. You can get a general estimate of where the problem lies by taking a good look at your CPU frame time for a couple seconds of simulation. For example, if your CPU frame time is around 16 milliseconds, then your game is running pretty well. Now, while your goal is to keep things under the 16 millisecond mark, some frames your CPU load changes and you expect slight variances in the time. If, however, your frame time starts to spike suddenly and your CPU computation load hasn't changed, you haven't put 200 zombies on the screen, then there's a high probability that this is due to the GPU getting backed up, forcing your CPU time to stall in the driver. These tall spikes are actually pretty telling, since they're around 11 to 15 milliseconds in time, which would be exactly how long the GPU would need to flush a frame or so. In order to figure out what the culprit really is, it's time to sit down and get proficient with mobile profiling tools. Some of the nuances of the GPU performance require dedicated tools to discover, but thankfully, each Android chip manufacturer provides a great suite of tools to give you more information on how to optimize your game for their hardware. Understanding and optimizing the dance between the CPU and GPU is the first step in maximizing your game's performance, which of course results in happier users, which could result in better transactions, and that's the whole point, right? So keep calm, profile your code, and as always remember, perf matters.
You started an online store and the customers are rolling in.
Your website is functional art, your ad campaign's gone viral, and the shopping carts are filling up. Your products have universal appeal. And you notice, hey, I'm huge in Japan. You're getting lots of international traffic, but it's not converting into sales. Why is that? After examining your analytics data, you see a lot of items getting abandoned during checkout. Do your international users just have a shorter attention span? Or is there something suboptimal about the user experience that is frustrating their urge to consume? We're going to address these questions and elucidate some of the famous question marks that beget profit. Have you ever seen an address in Japan? Let's start with something easy for me as an American. Here's where I work in Los Angeles. But here's where Googlers work in Japan. Let's remove the language barrier for a second. As you might notice, we're not in Kansas anymore. The order of this address is almost completely reversed from Western conventions. But you're smart. You can handle this. You whip out some JavaScript and manipulate that DOM. After a careful reading of Wikipedia, you are pretty confident. You can deal with users coming from Japan, shuffle your address around to make sure they feel right at home. Remove any impediments that might prevent them from obtaining the latest in wearable tech for their pets. But wait a second, every country does things a little differently. How many countries are there in the world? I don't know, a bunch. You're going to be up pretty late tonight, scouring the web for this sort of information for every country that likes cats. That's problem one. Now, here's problem two. Here's that address again, but this time it contains a typo. Can you spot it? I can't either. But users love typos, almost more than their cats. So you better figure out how to verify the address as it's being entered. Yo. Okay, I will end this rant. I hope you're convinced. Addresses are hard, and you just want to go shopping. But it's okay. Chrome's Request Autocomplete gives you all this and more for free. Request Autocomplete is a brand spanking new member of the HTML standard. And today, you can find it on Chrome for desktop, Chrome OS, Android, and iOS. And it's super easy to integrate into your site, which is nice. Request Autocomplete remembers your address, so in practice, most of the time you won't need to enter a new one, but when you do, here's what it looks like on your phone. It's native UI. So this is straightforward to use as an American. You can put in your name, my city, all that stuff. That's well and good, but here's the hard part, Russia. As you might have expected, the address fields look quite different from the United States. For example, you see the postal code and the city fields on top of the street address and the name fields. What about validation, you ask? No problem. Request Autocomplete can do that as well. Fantastic. Best of all, next time my address is ready and waiting for me. So, Chrome handles address input, data validation, and more while you focus on your product. Want to add Request Autocomplete to your site? Check it out here, or point your browser here. Easier internationalization is just one reason why Request Autocomplete rocks. The team is working hard to improve the checkout process for your users. Our goal is to help you maximize conversions and optimize the payments experience for the web, especially the mobile web, because let's face it, this resource is occupied. Until next time, I'm Ruslan Salamakin, and I'm huge in Japan.
Hi, I'm Alex Danilo from the Google Developer Relations team. One of the things I found really hard as a web developer is making compelling animations on a site. It seems easy enough at first to throw some CSS animations onto a site and watch the browser fly stuff around you and you feel all chuffed when you first see it. But if you're like me, you want to make your site really stand out, be memorable, not just another pre-canned clone of something people have already seen. So I started experimenting with different web animation techniques and right away hit problems with doing fancy things. Like for example, I wanted to make two things animate in perfect sync, but couldn't find a way to do it really easily. My solution took 1,000 lines of code and was extremely choppy and riddled with jank. If only there was a better way. Now this is the kind of thing I wanted to build, a 3D hardware accelerated view of the world with silky smooth, jank-free animation and total control. Well, now there is a better way. A bunch of browser writers and animation experts got together a couple of years ago to look at this with a fresh set of eyes. Lots of eyes, in fact. We spent a lot of time discussing what web developers need, how animation designers work, and a whole lot more. What we came up with is Web Animations 1.0. We aim to take all the existing web animation primitives out there and unify them, and also bring new capabilities that weren't just more powerful, but would run faster and smoother as a result. Now, one of the best APIs to play with animation from JavaScript is, of course, Request Animation Frame, especially if you want fine-grained control of everything that's happening on a frame-by-frame basis. So let's take a quick look at how animation works when you use Request Animation Frame. Now, using Request Animation Frame gives great control, but forces JavaScript execution on every frame. Now, this is fine if you're not doing much in your JavaScript, but we only have 16 milliseconds for each frame, and that includes paint and layout time too. So if you run out of time, you know what happens? Skipped frames, resulting in jank, which some people call jitter. Now, this is the main reason it's a good idea to decouple the animations from JavaScript execution itself. So we wanted the flexibility of control from JavaScript, but not the jank, and so this is what we designed. The Web Animations API lets you create animations from JavaScript, then offload the animation calculations to the browser so it can take care of all the heavy lifting for you. And in many cases, it can take advantage of hardware acceleration, so there's very little work to do for each frame. Now, what this means, it enables proper hardware accelerated animations to happen via the use of a JavaScript API, but without the slowdown from recalculating lots of stuff each frame. This is something we didn't have before, which is pretty cool, huh? I know what you're thinking. Yeah, but we already have CSS animations that are hardware accelerated. Right, well that's true, and by unifying everything, we extend the reach of hardware acceleration. The Web Animations design brings together CSS animations, transitions, SVG animation, and JavaScript created animations all into one thing. In fact, the Web Animations engine is currently used to run both CSS animations and transitions in Chrome. You probably didn't even notice when that happened, and that's testament to how seamlessly the Web Animations engine integrates into browsers. Now, even better is that in addition to powering CSS animations, you can call element.animate, which creates an animation player object that's used to interface to the animation internals inside the browser. Now, the object return lets you query and modify the running animation, so you get decoupled running of animation in the browser, but retain the ability to modify running animation from JavaScript, kind of the best of both worlds. Now remember this, the cool 3D globes actually built using Web Animations. Bet you didn't guess that. And it's just the tip of the iceberg. Here's another demo which shows how you can manipulate a running animation using input like touch. Now you can't build something like this using CSS animation, since there's no way to dynamically manipulate a running animation once it's started. But with Web Animations you can. And here's another which shows true synchronization, something almost everyone I've talked to is excited about. Web Animations are so cool, and you can use them right now. Not only does Chrome have native support for Web Animations, but we launched an open source implementation in JavaScript, which lets you use the API in any modern browser. That polyfill lets you use Web Animations right away, and we're doing all of this work in public at the W3C to make sure all browser vendors are on board. So take a look at the polyfill, the demos, hack through the code, make your site shine with the most powerful animation primitives available to web developers today. I know you'll blow people's socks off. I'm Alex Danilo. I'm excited to see what kinds of things you'll build using Web Animations.
Google and Udacity have teamed up to bring you a series of cutting-edge technology courses. Today, we're announcing 4 new courses developed with Google. In Android, Cloud, Web Performance, and UX Design. For more information, visit udacity.com/Google.
Hi, my name is Pong Ying, and I work on the Google Wallet team. I'm here to talk about the Wallet Objects API for native Android. I used to have a keychain full of these, different loyalty cards to take advantage of discounts and rewards. And these, I usually just end up leaving at home, unfortunately. I could have saved so much money. I don't think anyone but the most dedicated savers carry around all of their loyalty cards and offers all the time. To make it easier for everyone to carry around everything, Google provides the Wallet Objects platform. Wallet Objects is a concept of digitizing and storing all of your items in your wallet in the cloud and making them accessible from anywhere. And combined with a mobile app that has contextual information, we can make these items smart, so they appear when you need them. For example, I have a test object with a geofence of this building. Whenever I enter the geofence, my wallet object appears in Now, and it can notify me that it's available to use through an Android system-level notification. And we fine-tuned the contextual triggers so that these notifications won't trigger when, say, I'm just driving by the office. This functionality allows developers to do interesting things. Let's say you have an existing mobile user base, and you want to convert users from mobile to another physical medium. One example, it's a mobile game, and you want to convert the user to a console. In the game, you could add a geolocated wallet objects offer for a console title to incentivize user action. With the offer saved, the next time the user goes to a geolocation you specified, whether it's Fry's, GameStop, or Best Buy, or some other retailer, Wallet will notify the user that the offer is available to use. They buy the title, and boom! Now they're playing your game in the living room in addition to on mobile. Wallet objects can help with retail as well. Instead of all the coupons and offers that you need to remember to bring when you go shopping, you should just be able to save those offers from an app or from the web and have them notify you when they're relevant. Let's say I walk past a store in the mall and my phone notifies me that I have a coupon to save $20 off a purchase. I'm going to try to take advantage of that savings and check out if there's anything in the store that interests me. Cool. So you want to integrate, right? Let's go over how to create and save an object. The wallet objects flow is simple. You define the data representing the object and add a Save to Google button that calls our function createWalletObject with the object to save. The rendering is based on a template that gets populated by the information you define. To reduce redundancy, WalletObject stores data in two forms. It's somewhat analogous to programming. The class data represents information that's common to all users, like merchant details. The object data represents information that's specific to a single user, like a specific discount or a barcode. All this information is merged, then filled into the template. We have a number of fields here, and in this template, and any section without data is going to be hidden. Let's check out the code. First, we need to create the class. This code defines an offer class. We set the merchant and some offer details, some images, some subsections, and lat-long geolocations. Finally, we insert the class. Inserting the class needs to use a server-side REST API. Once you've created and inserted the class, you can create the object data in your Android app. This may look like a big wall of code, but it's your standard builder pattern defining an object. Here, I'm referencing a class I just created. I'm overriding some class fields and defining information that's specific to the user, such as barcode and messages. Once I have that, we can tie the object to a createWalletObjects call and tie that to an image button click, and we're done. So if you want to remind and incentivize actions for your users, integrate the WalletObjects API into your app today. For more information on the integration and a step-by-step tutorial, check out our developer documentation. I can't wait to see what you build. I'm Pong Ying, and thanks for watching.
Hey guys, I'm Eric Beitelman. I'm a staff developer relations engineer working on Polymer at Google. So in this video, I'm going to talk to you about how you can use Polymer and web components to interact with some of Google's most popular APIs and services just by writing a little bit of HTML. You know, the other day I was thinking, how many APIs does Google have? Do you know? I actually didn't. I had to do my research on this one. So it's over 250 APIs, things like Google Maps and Google Drive, spreadsheets, calendar, analytics, you name it, Google's probably got it. And of course, we all know that creating complex web applications requires you to interact with APIs and services. So on the Polymer team, we've been thinking about this a little bit. How do you combine Google's awesomeness with the world of web components? We really want to make working with web components as easy as writing a little bit of HTML. That's really the power of web components. And it turns out they're a great delivery vehicle for wrapping existing content, libraries, and services. Think of it as a way to declaratively provide a declarative surface area for the API that exists. This is really where Polymer comes in. For those that don't know, Polymer is a bleeding-edge technology. It's a library built for the web and allows you to create web applications based on web components. But to me, what Polymer really does is provide a thin layer, of opinionated layer on top of the web component APIs. So we built in things like data binding, property observation, gesture support, mobile support. These are really important when you're building applications. We want to make it easier for you to ramp up and use. So we built that into Polymer itself. You know, a popular API is something like Google Maps. It's very complex, it's very rich. So let's take a look at how web components can actually make your life easier using that API. This is Google Maps Hello World, right? It's pretty simple, but there's a little bit of boilerplate code that you have to write every time you want to render just a map to your page. You have to know to style it using a little bit of CSS. You have to know that there's a container div that you need to create. You have to load the library. You have to remember that. You have to work with loading and callbacks and write a little bit of JavaScript. Point is, there's a lot of process you have to go through to get this thing kicking. So let's see what we can do with web components. In the world of web components, this is the Google Maps API. It's a single tag you declare on your page. That's ridiculous. Ridiculously awesome. You declare it and you're off to the races. And it does exactly what you expect, which is render a map to your page. It's simple, it's declarative, it's intuitive. I don't have to write JavaScript code. I don't have to know about callbacks. I don't have to read API documentation. You get my point. You just use this thing and it works. But Google Maps, right, is an extremely complex API. So instead of writing JavaScript, what we can do in the world of web components is expose attributes on this element for people to configure the different properties and methods that the API exposes. So for instance, really common thing to do, latitude and longitude, set the center of the map. We can do that now using that latitude and longitude attributes. We can also set the zoom level of this map just by setting the zoom attribute to 15. That's really awesome. Again, it's all declarative and super intuitive. You can read this code and know what's going on. And adding markers is just as easy. It's just as declarative. So we can drop in a bunch of Google Map marker elements inside of the Google Map tag itself and compose these in different ways. The fact that the marker tag is in the map is significant. It knows to render that marker to the page. I'm also reusing other parts of the platform here. So you notice I didn't reinvent the wheel for the title attribute, or I didn't reinvent the wheel for the drag and drop API. I'm using the draggable true attribute. So again, I can reuse parts of the web platform that already exist. I don't have to reinvent that wheel every time I start a new project. That's cool. The other thing I really love about this element is that it makes some of the API complexity go away. So one thing that's really common to do in the world of maps is center your map inside of the viewport of all the markers that contain inside of it, right? Make sure they're available to the users at all times. That's a little bit of boilerplate code, a little bit of JavaScript that you have to know how to write every time you want to do that. You add a new marker, you want to update the map. Instead, what we can do in the world of web components is, again, expose another attribute, this fit to markers attribute. So as long as I have that on my marker tag, my map tag, boom, the map just updates itself. It knows to set the zoom property accordingly. That's Google Maps. It's super declarative, super easy to use. But you can imagine a ton of other use cases here for all the APIs Google has, whether it's working with charts or spreadsheets, analytics. Anything can be a web component. We can provide a declarative surface for people to tap into that. And that's exactly what we've done. So we've been experimenting with this over on GitHub. If you want to check it out, Google Web Components is the GitHub organization. We have a growing collection of awesome components there. Things for analytics and maps, you saw, Google Spreadsheets. We also have base components for doing more low-level things, working with the libraries that Google has, doing OAuth 2. God knows that is very complex. So just like Maps, these are super declarative, super easy to use. Check them out. If anything is missing, let us know. We're really interested in getting your feedback, getting pull requests, and adding new APIs and services all the time. So actually, let's use this. Let's combine proof in the pudding, create an application that uses Google Maps and Google Spreadsheets. We'll create a Polymer element that wraps all that together, and users can use that element inside of their own applications. Oh yeah, I almost forgot. We're not going to write any JavaScript to do this. We're just going to write a little bit of HTML. So if you're curious, this data is going to be coming from a Google spreadsheet. This is what the data actually looks like. Essentially, it's just a list of businesses in Portland, Oregon, right? There's a little bit of metadata, but the most important thing here is that we have the latitude and longitude columns. This is the data that's going to render those marker objects. So the first thing we do, we got to bring this stuff locally into our app. We're going to use Bower to install it. We're going to Bower install the Google Map tag, and then you see the example here, which we've already seen, so let's move on. What you haven't seen is the Google Sheets tag. This is an element for working with Google Spreadsheets. We're also going to Bower install that, bring it in locally to our application. And the second example here is how you actually use this element. So again, it's super declarative. I declare Google Sheets, and boom, I'm off to the races. It's got a publish property, which essentially means, hey, this data is being published publicly. Don't worry about doing authentication, it's just there. GID corresponds to the tab in the spreadsheet that I want to interact with. So GID 0, first tab. And the last thing we're doing is providing a spreadsheet key. And you see the example here where you actually get the key is in the URL bar when viewing this spreadsheet in Google Docs. So it's super easy to use. And the last step, if you're outside of Polymer, you just have to write a little bit of JavaScript to maybe listen for the event that this element fires and then react accordingly. So in this case, we can print out the data that the spreadsheet returned. But it's really that easy. Declare, go. So now that we have those dependencies installed, right, Google Maps and Sheets, let's actually use them. Let's create a Polymer element that wraps that functionality together. This is the entirety of the application. Let's walk through these pieces. So the first thing, now that we have the dependencies installed, you want to list them at the top of your file. So this is using HTML imports, which is one of the web component APIs. We're going to list Polymer as a dependency, the Google Sheets as a dependency, and Google Maps as a dependency, now that they're in our application. The second thing we're going to do is create a Polymer element. So this is using Polymer's declarative sugaring to do this. The name of the tag we're going to create is map-sheets. This is what somebody's actually going to declare on their page when they use our stuff. The second thing you see here is this no-script attribute. That's essentially just a hint to Polymer to say, hey, I'm not going to add any properties, any methods to this. It's just going to be a little bit of markup that we're essentially repackaging for users. So it's a pretty simple element. Inside the elements template, you're going to drop in that Google Sheets component. This is what's going to talk to our spreadsheet. You can see I got the key there. I got that publish attribute, and we're data binding to the rows attribute that this thing has on it. More on that in just a second. Right below it, we have the Google Map Sheet. This is your friendly tag that we already know about. Notice that we're using that fit to markers attribute that we talked about before. So again, anytime I have extra markers being rendered in this map, it's just going to know to set the zoom level to the appropriate level. Lastly, what we're doing is we're using Polymer's declarative data binding features to declaratively loop over the row data returned in the spreadsheet. So again, I'm not writing any JavaScript code to wire this stuff up. I'm literally just declaring a template, looping over the data, and stamping out Google Map marker children. And of course, we're data binding that latitude and longitude property to the particular cell that we're interested in. So again, it's all super declarative, and the surface area is just using HTML attributes. So that's the entirety of the application. If somebody wants to use this, it's just a matter of bringing in Platform.js, right? These are the polyfills that actually allow you to use this stuff in browsers that don't support the native APIs. Check. You want to declare the Google Maps sheet as an HTML import. That's going to bring in the element we just created. Check. The last thing you want to do is just declare the Map Sheets tag on your page. And of course, what people get is this beautiful map, marker data, all powered by Google Spreadsheets. We didn't write any code to do it. We used Polymer web components. That's the bee's knees. So if you want to see a live demo of this, go check it out. It's at googlewebcomponents.github.io. We have this demo as well as a ton of other demos for all the other components we've created. So that's a small taste, just a small taste of what Polymer and web components can do. I really think web components are going to unlock a fundamentally new way to program for the web. You've already seen it's productive, it's declarative, it's reusable, and you can vastly reduce the amount of code you write as a front-end developer. That's really, really awesome. So if you want to know more about creating applications using Polymer, do check out Rob Dotson's video and Eddie Osmani's video. These are a couple of stellar guys with some really, really great content. Check us out on polymer-project.org. This is our website, powered by Polymer, of course. And follow us on Twitter at Polymer. You can also feel free to hit me up anytime, ask questions. I'm always on Twitter. I'm on Google+. Oh yeah, one last thing. Go componentize the web, guys. Thanks for watching.
Hi, I'm Jarek Wilkiewicz, and I'm a developer advocate. I was born in Poland, and like many other engineers, I grew up reading science fiction. In fact, this is my favorite author. My childhood home was actually very close to his house in Kraków, and little did I know that his work would have major influence on my life. Did you read science fiction too? Do you remember the moment when the protagonist, while busy saving the world, asks her computer for something? Computer, make it so! And the machine just does it, and it nails it. Now, why can't the real world be more like this? For example, when a user says, "OK Google," and asks for something, the application or service most suitable to fulfill the request should be invoked and get the job done just like that. Today I want to talk to you about technology based on schema.org actions, which I think is a small step in that direction. With actions, we have an opportunity to delight your users and bring more engagement to your app. However, we can't do it alone. We need your help. At Google, we have been working on organizing the world's information to make it universally accessible and useful. To help with that, we've built the knowledge graph. The knowledge graph contains information about entities and their relationships. One of the interesting applications of the knowledge graph is resolving ambiguities when processing language queries. For example, the artist dual core is a band, which is different than the concept of dual core. As far as the strings are concerned, these two are equal, but to a user who is asking their phone to play dual core, the difference is quite clear. Dual core the band is assigned a machine ID in the graph. We like to refer to these types of object-based identifiers as things, not strings. Having a graph entity with a machine ID, OMID, makes a big difference. The knowledge graph can also help satisfy user requests with your application. I thought a good way to show you how this works is to actually build a small knowledge graph together with you. But first, let me introduce you to my buddy, Sean. This is Sean. We both like music. Sean likes to DJ and spin dance LPs in his free time. One day, we would love to open a record store. We would curate an awesome selection of LPs, and on weekends, we would invite our favorite artists to give concerts at our store. Now, wouldn't that be great? Our music selection would, of course, be available for purchases online. We would offer web and mobile streaming access as well. Since today, most music recommendations are provided by computers, we would want to make it easy for computers to discover and understand what we have to offer. For example, when the user says, "OK, Google, play dual core," we would like our app to be ready to fulfill users' request. All right. So we have this music store. We are selling LPs, offering streaming access, and hosting events on weekends. How do we express this information in a machine-readable way? And how will it be used? Let's look at a simple architecture diagram. The flow of information is illustrated by the direction of the arrows. As you can see, the crawler fetches data from our music website and saves it in the knowledge graph. The graph is then consulted when a user issues a voice command or a web search. Sean and I publish this information about our music artists and albums on our store website. Now, how do we do that? Rather than inventing a new publishing format, we will apply the linked data principles. The term linked data refers to a set of best practices for publishing and connecting structured data on the web. We will use schema.org vocabulary and JSON-LD serialization to describe the entities in our music store. If you haven't heard about JSON-LD or schema.org, don't worry. Click the links on the screen or follow along. It's pretty straightforward. For example, here's what an artist looks like in JSON-LD. The JSON-LD markup is embedded in an artist's web page on our site. Now, take a look at the same as property. This property will make it easier to reconcile or match the JSON-LD document describing an artist with a corresponding entity in our knowledge graph. In the spirit of linked data, the same as property links the artist with information on another site. This stuff is pretty important, but we'll show you more about how that's used in the next video. As I mentioned earlier, we built a mobile app so our customers can enjoy music on the go. How do we express the fact that our music artist we carry can be listened to using our app? Remember, I want our mobile app to be triggered by the OK Google voice command. Fortunately, we can also use schema.org and JSON-LD for that. A recent addition to the schema.org vocabulary makes it possible through something called potential actions. Here's an example. Note that in our markup, we are making an association between an artist and a mobile application we have built. Let's recap. Sean and I described our store using JSON-LD and schema.org. So now this information is machine readable. We have also associated our music app with artists that it can handle. Does this mean that our music app will now be triggered when the user asks Google to listen to the music we have marked up? Not quite. First, we need to test. There are several things that can go wrong we want to verify. The crawler has to be able to parse the JSON-LD markup we have published. Artists described in our JSON-LD documents have to successfully reconcile or match with entities in our knowledge graph. Our mobile app has to handle specific intents so that the music starts playing when the app is triggered. Quite a few things to test, isn't it? Don't worry. To help you with testing all this, we have provided sample open source implementations of the components you see highlighted in this diagram. The website, the mobile app, the crawler, and the small knowledge graph running in a graph database called Kaylee. We have also built a mobile and web simulator to help you trigger the schema.org actions defined in the JSON-LD documents for the music store. All right, what do we do next? Now that our JSON-LD markup is on our music store site, we can run the crawler to make sure our markup is correct. The crawler parses the JSON-LD markup and transforms it into a graph database called Triples. It looks like this. If this sounds intriguing to you, it sure is for me. See the second video where my colleague Barak will show you how the output of the crawler can be loaded into an open source database called Kaylee. Barak will also show you how you can join the music store data with Freebase, a free structured data repository with millions of people, places, and things. If you would rather skip ahead and learn more about how the entities published on our music store website work in conjunction with schema.org actions, see the third video in this series. Better yet, clone the repository that we have shared and play around with the code before you proceed to the next video. Thank you and have a great day.
Mobile developers and designers use different approaches to achieve the same goal: creating 5-star apps that users love. While both development and design approaches are essential, they are usually considered separately. In User Experience Design for Mobile Developers, you'll learn how to integrate design approaches and techniques into your mobile development to build world-class apps. This is a design course for developers who want to give their users a great experience. For more information, visit udacity.com/Google.
Everything has a location, whether it be the photos you took, where you are, the places you like to hang out, where you bought that special gift, or even the last place you met your date. I'm Megan Boundy, Product Manager for the Google Maps mobile SDKs. Today I'm going to show you some cool ways to use Google Maps mobile SDKs to help you both bring these experiences alive and delight and engage your users. In this session, I'm focusing on the Google Maps Android API v2, but all of this functionality is available in the Google Maps SDK for iOS as well. This is great if you're looking for cross-platform consistency for your apps. When developers think of having a map in their app, they often think of something like this: a marker on a map. This is great for showing your location or marking out where you might want to meet someone. But did you know that you could add Street View to your app like this? Or make cool apps like Santa Tracker that follows Santa around the world as he delivers presents? Let's take a look. Our docs show you how to embed a Google map in an Android activity. Then it's easy to add markers to your map. You just use the add marker method and specify a few options to customize the marker. For example, you can set latitude and longitude, change the color of the marker. You can also set what shows up in the info window when the user taps the marker and the info window pops up. You may even want to use photos as your marker. Maybe you want to show where the photo was taken on a map and associate it with an event, rather than just showing a strip of photos in your app. Now that you've seen markers, let's take a look at Street View. Most excitingly, you can add Street View imagery to your apps. In this demo, you can see the split screen with the Street View imagery in the top half and the Google Map in the bottom half. By long pressing the marker and dragging, Street View imagery updates and shows you the location where you drag the marker to. So how do you do this? A very similar demo is available in the demo examples in the Google Maps for Android API v2 itself, so the code is all there. Here we've split the layout into two parts. It's one fragment for the Street View panorama and one fragment for the Google Map. You then set the same initial location for the map, the marker and the panorama, and we've given our marker a custom icon, which is Pegman. When you drag the marker, you listen to a drag event from the marker and use the callback to position the location of the panorama. When the panorama change event occurs, the listener will give you the precise location of the panorama, and you can feed this back to the marker to update its position completely accurately. So what else can you do with Street View? You may want to add Street View to your store locator, see an area around a hotel, or view a museum or an aquarium. Street View also provides you with seamless access to Google's indoor Street View imagery. You can set the Street View panorama to be of imagery within the aquarium, or set it outside the aquarium and have your users navigate inside if they wish. Of course, you can do this for stores as well if the store has indoor business view imagery. This would be awesome if you're a store owner and you want your customers to see what's available inside to entice them to come and visit you. Okay, moving on. How can you make your users feel more immersed in their Maps experience? Have you tried out the Santa Tracker app and wondered why it felt so movie-like to follow Santa as he flies around the world? This is because we made the camera track Santa's location. Both the Google Maps mobile SDKs use a camera that lets you set the location of what you want to look at. You can animate the camera by using a camera update and calling the animate camera method. This is where you can also set the zoom level, the bearing, the tilt, and the duration of the animation. It's so effective. If you don't want to see any animation, you just call the Move Camera method instead, and it will move the map directly to that new location. We have a whole session dedicated to the Santa Tracker app at Google I/O 2014, so make sure to take a look. Now you know how to make your users feel more immersed in their Maps experience. How do you add things to the map and animate them? For example, how do those weather apps get the clouds coming in over the terrain map? Google Maps has several map types available, such as satellite, hybrid, or terrain. It's really easy to switch between map types. You just use the Set Map Type method on the map and specify the map type that you want. These apps are also using mostly transparent tile overlays with the clouds as the opaque features. Tile overlays allow you to specify particular tiles to be shown at a given set of coordinates. You should also specify which tiles can be shown at each zoom level. All you need to do is define a URL tile provider and supply that to the tile overlay options, then add it to the map. To make the clouds appear to be moving, the weather apps are swapping out multiple tile overlays periodically to make it appear animated. Talking about the weather, it may be time to go inside. There's also the ability to see indoor maps along with programmatic control of the indoor level of the building and the floor picker. You can find out which building is active by calling Get Focus Building, and then find out the active level of that building by calling Get Active Level Index. This is great if you want to show custom markup for the active level, such as markers, polylines, tile overlays, and other shapes. You can also turn off our default level picker and implement your own by passing false to the method Set Indoor Level Picker Enabled, and then adding your own. Now we've seen all parts of the world via our map: indoor, outdoor, street view, a normal road map, and weather overlays. Who knew you could do so much with maps in your apps? To get started mapping up your own apps, go here for Android and here for iOS. And if you need any help, our support page lists the Stack Overflow tags that you need. So what are you waiting for? It's time to get out there and start mapping up your apps.
Hi, I'm Lewis from the Google Play for Education team. In my experience as both a former middle school teacher and in working with thousands of teachers over the past 10 years to integrate technology, I've learned that schools and classrooms are a pretty unique environment. Vibrant, supportive, collaborative, nurturing, busy, perhaps even a bit chaotic are some words that come to mind. And diverse. Curriculum, classroom environments, and teaching and learning styles vary dramatically. Google Play for Education is a dedicated store designed just for educators that works hand in hand with our tablet program. Its features make it a great opportunity for educational app developers. Your app's success depends on whether it pays careful attention to the demands of the unique environment. Many of the principles involved in developing an app for consumers at home need to be rethought for the classroom. So in this video, I'd like to share 5 key considerations for optimizing your app for the classroom. I'll also tell you about some of the top requested features we've heard from educators. So let's get started. First, simplify your app by focusing deeply on a few aspects of the user experience. Here's why. Students will have very limited time to learn and use your app, and will often need to access your app quickly from multiple devices. For example, if a device has a problem, many schools keep a stash of extras on hand to distribute on the fly. Or students might use a different device at home. So here's a few aspects of your user experience to be sure to focus on. First, make sure your app can be learned without instructions or has a quick onboarding experience. Teachers won't have time to teach students individually how to use your app. Next, make sure your app works well in bite-sized chunks and that students can quickly pick up where they left off. Students need to be able to get in, use it for 5 to 10 minutes, and then move on to another part of the lesson. Be sure to test how well students can transition from one device to the next. So if you have a website that complements your app, be sure students can move back and forth from tablet to laptop and back really easily. Google Sign-In is a great way to do this, which I'll talk about later. And finally, clean up your UI. Don't forget that if your app might be used by little kids, say in kindergarten, make your touch targets large to help their little fingers out. Also, many students, even older ones, might not be able to read or might be English language learners. So use lots of visual cues or audio prompts. Walk into a classroom with an amazing teacher. You'll immediately see students that are deeply engaged. But where does technology fit in? We asked schools, and they told us that using Google tools is about more than technology. It's about adopting a culture that extends beyond the classroom walls. It's about openness, curiosity, and working together. Plus, learning should be fun. So to make sure your app supports an open and engaging classroom culture, consider this. Since students using your app will all be using tablets, are you taking enough advantage of the hardware's unique capabilities? Are you using the touchscreen in interesting ways? What about the camera, the microphone, or other sensors? Students should not just be staring at a screen. Does your app work well in highly collaborative environments? You might see a few students gathered around a tablet, or maybe 5 students, each with their own tablet, working together on a project. And lastly, can students use your app to learn by creating? Students need to apply their learning by building, being creative, and expressing what they know. Apps that enable this are much more engaging and also give teachers an authentic assessment of what students are mastering. So whether it's the sensors that are being used to take measurements for an experiment in science class, or students in English class that are making a video with their own dramatic interpretation of Shakespeare, be sure your app fosters student engagement. Teachers and students will use a variety of apps and tools. So be sure your app isn't an island by integrating with Google's platform APIs. The most common request we hear from teachers is that apps must integrate Google Sign-In. Imagine for a moment that you teach middle school math, which is what I taught, and have 180 students going through your doors every day, which is what I had, by the way, and what it'd be like to manage that if the kids had separate usernames and passwords for each app they used. Google Sign-In helps solve that problem. We've literally had teachers tell us that when they're looking for apps to buy, they start by first looking at only those with Google Sign-In. Easy authentication, it makes that big of a difference. Here's why. All students will already be logged into their tablet with a Google account. It's required as part of our tablet's setup process. So if your app authenticates with Google Sign-In, students can log into it with just a couple clicks. And 30 million students across the world use Google accounts as part of our Google Apps for Education offering for schools. So integrating Sign-In is also a great way to appeal to that huge base of users. The details on this OAuth-based approach are on our website at this link. Oh, and don't forget, if your app reads or writes files, be sure to also integrate with Google Drive, as Drive is incredibly popular among those 30 million students and teachers I mentioned. Many teachers use Drive sharing features as a way for students to collaborate with each other and to turn in assignments for grading. Teachers have incredibly hard and busy jobs with tons of constraints and demands. Even if your app's primarily focused on students, the more it can also meet the unique needs of teachers, the more likely they'll keep using it. So be sure your app aligns to the Common Core state standards in the US, and especially the increased rigor and application of knowledge that they represent. Common Core standards are learning goals adopted by 44 states that outline what a student should know and be able to do at the end of each grade. Our educator review process explicitly looks to see that apps align well to the Common Core. Plus, this will make it easier for teachers to find your app, as teachers can filter by standard right there in the store. So the next 3 suggestions go hand in hand: support differentiation, progress monitoring, and feedback. This type of personalization allows students to work at their own pace, but with support from their teacher. A great book reading app, for example, might allow a teacher to assign different students to different books based on their reading level. Then, teachers should be able to see key metrics for each individual student, such as what concepts they've mastered, which books they've read, or how much time they've spent on different topics. And allow teachers to give meaningful feedback to students right there in the app. Lastly, have an educator-friendly app description. Be sure to highlight standards alignment, differentiation capabilities, any other teacher features right there in your app description. For example, the description for slice fractions highlights the specific fractions concepts covered by the game, and it also includes a note to teachers. Lastly, this hopefully goes without saying, but be sure to test, test, test. Try your app on the various Google Play for Education devices. As of this video, there's 4 supported tablets, but be sure to check out our site for the latest. And be sure to try your app with real kids and teachers, and iterate constantly based on their feedback. Also be sure to check out our Google Plus education communities too, as they're a great place to connect with educators who would love to share their ideas with you. So to recap, here are 5 things to keep in mind to supercharge your app for the classroom and help teachers and students transform learning. Be sure to check out our site with even more info, with details about topics like safety, privacy, and data, monetizing and ads, more information about app quality and testing, and our Google Play for Education review process. And I can't wait to see your amazing educational app. We'll see you in the classroom.
Hi there, my name's Ellis, and this is Making Polymer Elements Accessible. So you've gotten the Web Components bug and downloaded Polymer and you've made your first custom element. Fantastic. Today, I'm here to talk a bit about how we can make sure our brand new custom elements can be used by everyone. Right now, built-in HTML5 elements work well for accessibility. This didn't happen by accident. Browser developers followed published standards for ensuring the accessibility of these elements and add keyboard handling, styling, and semantic information to make sure that all users can use them. When we're creating new components for the web, ideally they should be using the same standards. They too should be accessible to all users. When we talk about all users, there are several broad classes of impairment that we consider. Visual impairment, which could range from poor color vision through low vision to no vision. Hearing issues, whether a user is deaf, hard of hearing, or simply can't use their device's audio output. Mobility or motor impairment, whether temporary or permanent, such as a broken arm, RSI, or long-term motor disorder. Other impairments, which encompass a very broad range of issues, including cognitive impairments like dyslexia, ADHD, brain injury, and other impairments like learning disorder, epilepsy, and vestibular disorder. The first thing we want to look at is whether our element can be used with the keyboard alone. This is a first step ensuring it can be used by users of assistive technology on all platforms, but also important for users with motor impairments or injuries, or any desktop users who can't or won't use a mouse right now. During your user experience design, think about how you would use your element with the keyboard alone and figure out a consistent set of keyboard interactions. To help with the design process, consider including physical impairments in your user experience personas. If you're creating an element which mimics an existing element in some way, consider copying the way it handles keyboard interaction to provide consistency. Try using a native element with the keyboard and find out what already works. Chances are you've been using the keyboard sometimes anyway, so you'll find it comes pretty naturally. Later we'll talk about ARIA, which allows you to specify additional semantics for your element. Once you've picked a semantic role, you can use the ARIA Design Patterns Guide to get some extra advice on what keyboard events to handle. The first step in actually implementing keyboard interactions is to make sure the element can take keyboard focus. Unless you can actually focus on the element, it's not going to get any keyboard events. Ensure you have a sensible focus target for your element. For a simple element like a button, this will obviously just be the element itself. A complex element like a menu may be one focus target within the page, but then manage focus within itself, so that the active menu item always takes focus. In this case, you want to make sure that the menu items are programmatically focusable, but not in the tab order itself. This is where an understanding of the nuances of the tab index attribute is going to come in handy. Tab index can take one of 3 classes of values. When tab index is 0, the element will be in the natural tab order, which is defined by the DOM order. This is what you would use to make a custom element, such as a custom button, keyboard focusable. When tab index is negative, the element will be programmatically focusable, but not in the tab order. This will be useful for something like the menu example on the previous slide. The menu container element can manage setting focus to each individual menu item when appropriate. The tab index is greater than 0, the element will be in a manual tab order. This makes no sense in the context of web components, since you essentially never know where your element will fall on the page. So now that you've spec'd out your keyboard interactions and made your element focusable, you need to implement the actual keyboard interactions. Luckily, there's an event handler for that. You can add an on-key down attribute to your Polymer element and add a method to handle the keyboard event, checking for any key press events you're interested in. Finally, make sure your keyboard interactions are discoverable, especially if they're not using one of the standard patterns. Tooltips or keyboard help overlays are common patterns for achieving this. Once our keyboard interactions are working, we're a good part of the way there already. Next, we need to take a look at whether our element can be used with assistive technology. The types of users who would use assistive technology range from users with visual impairments who might use screen readers or braille displays, to users with cognitive impairments, such as dyslexia, who might use a screen reader to augment their reading ability, and users with motor impairments who need to use technologies like voice control to interact with their devices. There are really only two parts to ensuring that your element can be used with assistive technology, including screen readers, once you've addressed keyboard accessibility. Adding semantic information, including the element's role, state, value, and name, and making sure that all information conveyed visually has a text alternative. First, let's talk about semantics. One of the great things about custom elements is that they make our markup look semantic again. We can hide presentation logic inside the shadow DOM and use meaningful element names to create a readable DOM. However, assistive technology doesn't see those semantics. It still sees, essentially, div soup, unless you tell it about the semantics you want your element to have. Assuming we're not extending built-in elements, the way we tell assistive technology about these additional semantics is using WAI ARIA, or ARIA for short. ARIA is a specification defining support for accessible rich web applications. It defines markup extensions implemented as attributes on elements, which can be used to provide additional information about the semantics of elements to assistive technologies like screen readers. This is what using ARIA looks like in vanilla HTML5. So we can use ARIA to add the semantic information we want to our custom elements. This is a custom slider element, which you can visually see has a minimum value of 1, a maximum value of 5, and a current value of 2.5. Until we add the relevant ARIA attributes, though, this element doesn't communicate any of this to assistive technology. We can add ARIA value attributes to tell assistive technology about the value of this element. Here we've added the attributes for role and current minimum and maximum values. Finally, once all your semantics are in place, make sure you always have text alternatives for any other information which is conveyed visually. For example, if your custom button uses a settings icon, make sure you give it a name of settings as well. And obviously, make sure all of your images have an alt attribute, even if you want them to be skipped by assistive technology. Assistive technology will try to come up with alternative text if you don't provide it, and often it'll pick the file name. So provide an empty alt attribute if you want the image to be visible to assistive technology. We also need to make sure that users with any form of color blindness can use our element. Firstly, this makes sure that we're not communicating anything with color alone. Color shouldn't be used as the only means of conveying information, such as indicating a status, prompting for a response, or distinguishing a visual custom element. Here we have the Chromium dashboard, which, as well as being a Polymer application, gives a status for each new web platform feature being developed or shipped in Chromium. Since the color dots next to the stakeholders are meant to convey information, the developers added a tooltip here, which appears when you hover over the name giving the same information. We also need to make sure that there's always sufficient contrast between text or icons and the background color. This is important for users with low vision who might have trouble reading low contrast text, colorblind users in the case where we're using two different colors next to each other, and any user using a mobile phone or device in bright sunlight. Any text content displayed in your element should at least meet the minimum contrast ratio of 4.5 to 1. You can audit your element for sufficient contrast using the Accessibility Developer Tools extension, which even provides suggested foreground and background color pairs if it finds low contrast text. Lastly, make sure any moving or flashing content is stoppable and safe. If you have any fancy slidey, parallaxy transitions, make sure you have a way to turn those off. They can be a real pain for people with vestibular disorder who may experience motion sickness symptoms while using them. And if you have any flashing content, please don't tell me you're re-implementing the blink tag. Make sure it meets the criteria for safe flashing content of having a flash frequency of 3 times per second or fewer. So let's recap and summarize everything into a handy list. Remember, every built-in HTML5 element will have all of these properties, at least in a mainstream browser, so we should make sure that custom elements do too. Make sure that your element can be used with a keyboard alone. Make sure that it works with assistive technology. Make sure that it doesn't rely on color to communicate important information. Make sure all text and icons have sufficient contrast ratio with the background. Make sure that it works without sound. I didn't cover this, but make sure any video or audio elements have the appropriate text alternatives, and make sure you aren't relying on audio cues to prompt for actions. And finally, make sure any moving or flashing content is configurable and safe. Please
Hello? Hey, everyone. I was really hoping we were going to run into Justin Bieber's soundtrack. They had some great music playing. I was hoping we were going to break through a wall or something, but,
yeah,
you know.
Keep the music playing. I was enjoying that.
Welcome, everyone. We have the dubious 1 p.m. after lunch hour session. We hope that you're going to be as excited for this presentation as we are. The title of this is Making Your Cloud Service Google Fast. Some quick intros. My name is Weston Hutchins. I am a product manager on the Google Cloud Platform team.
My name is Mandy Waite. I'm a developer advocate for the Google Cloud Platform.
She's my dev rock star for today. And today's talk, you know, it's really hard to talk about a topic as deep as performance in 30 minutes. So Mandy and I have cherry-picked a few tips and tricks. We're going to show you guys some demos on top of Google Cloud Platform and how we can make your app as fast as possible, leveraging the infrastructure we use at Google. So we've broken down this into 4 topics. The first is I'm going to tell you a little bit about why fast matters. Then Mandy's going to take over and tell you how we think about fast inside Google, how we leverage the infrastructure to build our world-class apps today. Then the meat of the discussion is going to be around two topics. One of them is measuring fast and how you should think about correctly measuring the performance of your application. And then Mandy's going to take over and tell you guys how to scale out and scale fast so you guys can be the next secret app that has, you know, 1,000x growth in your first month of use once you reach the front page of Hacker News. So why fast matters? You might be thinking, duh, I mean, of course it matters. But I always like to throw out some fun facts just to talk a little bit about what the impact of performance can have on your users. There was a study done a little while ago that Google actually went out and intentionally induced a server-side lag delay for every result that was coming into the Google search page. And they wanted to measure the behavior over a period of 3 weeks of how often users were searching with various amounts of lag built in. And what they found was pretty interesting. If you just increase the amount of lag by 400 milliseconds, it would reduce the amount of searches by 0.6%. And when you're talking at Google scale, that's actually a huge number. It ended up being about 8 billion searches a day at the time this study was run. Even more so, this study also figured out that users are impatient. And you guys probably don't need me to remind you about that. But they found that 1 in every 4 users will abandon a web page if it takes more than 4 seconds to load. And given the competitive nature of performance nowadays, I can only imagine that this number is likely to decrease over time. Mobile apps are also important as well. It's not just websites that we have to start thinking about. There was a study that was released just this last week by AppDynamics, which is a leading performance monitoring solution out there. What they found when they surveyed a bunch of users was that performance was the #1 top frustration when using mobile apps and websites. 86% of users deleted or uninstalled at least one mobile app because of problems with application performance. Now, there is a silver lining there. They also found out that when users are happy with your performance, they're going to spend more money. 30% of users said they would spend more money with an application that had greater performance over its competitors. So there is real incentive here for you guys to spend the money, spend the time speeding up your application and making it fast for your end users. And with that, I'm going to hand it over to Mandy, who's going to talk about building a culture of fast at Google.
Thank you, Wes. So fast is at the core of pretty much everything that we do at Google. Well, nearly everything. And users of our products and services are used to experiencing a consistently fast performance from all of our products and services. You can offer that same experience to your users by using Google Cloud Platform, because Google Cloud Platform runs on the very same infrastructure as services such as Gmail, Google Search, YouTube, and all of our other products and services. So let's talk about some of the philosophies behind FAST at Google. In order to meet the demand of modern day applications, the traffic demand of modern day applications, you need the ability to scale fast. And scale fast is something we're going to talk about in the last section, as Wes has already mentioned. And App Engine, our platform as a service offering, which we'll also talk about shortly, that kind of epitomizes the notion and the principle of scale fast. So we have an example of that coming up soon. The ability to measure fast allows you to gain insight and understanding of the very complex nature of modern-day applications running in the cloud. And Wes is going to talk to you very shortly about some specific examples around latency, and also introduce you to some tools that we're going to be making available to users of the Google Cloud Platform. And then there's the ability to innovate fast. Now, this has really been core to our ability to actually keep ahead of the game when it comes to handling the, as you can pretty much imagine, handled the massive amount of traffic demand that we have on all of our products and services. And not just on the products and services themselves, but also on the infrastructure that runs them. So we've innovated rapidly over the last 15 years. And this is a timeline of some of the things that we've introduced, white papers and such like. Bigtable is our massively scalable NoSQL data store. And many of our services use Bigtable directly. And in fact, App Engine itself was built around Bigtable. It was actually built around Bigtable to use it specifically. So users of App Engine had direct access to Bigtable as the App Engine data store. That data store has now been made available to users of the Cloud Platform directly from anywhere, any user from anywhere, from any application, as the Google Cloud Data Store. Then there's Dremel. Dremel is an analysis tool that allows you to run interactive queries across massive data sets. And we're talking about terabytes here, billions and billions of rows of data, and to get results back in seconds, not minutes or hours, as you would do with a MapReduce. Dremel is available externally via the Google Cloud Platform as the BigQuery service. Then there's Colossus. Colossus is our second-generation file system, and many of our data services are built on top of Colossus. Colossus has been made available to Cloud Platform users for many years now as Google Cloud Storage. Then there's innovations at the infrastructure layer, and we're going to talk about Andromeda shortly. So we have scale fast, we have measure fast, and we have the key of innovate fast. All of these things make to a wonderful Google Cloud Platform experience when you use it. Not only do you get all of these when you use Google Cloud Platform, but you also get fast connectivity to the rest of Google at no extra cost. So if you want to consume Google search results, YouTube videos, maps data, finance data, you can do so at no additional cost. If you were using another cloud provider, you would probably have to pay some additional charges in order to get that data into the cloud. So I want to talk about how some of the changes that we've made to our infrastructure will benefit Cloud Platform users. And I'm going to do this in the context of a product, not a product, a feature of our network infrastructure, our network virtualization layer called Andromeda. And Andromeda provides all of our virtualization needs. So Andromeda is our network-based, SDN-based, software-defined networking-based network backbone infrastructure. It provides many benefits to us in terms of quality of service, fault tolerance, and lower latency. But it also provides all of our virtualization services, and that shows up in the form of virtual networks for Google Cloud Platform users. Now, Andromeda was not built as a Google Cloud Platform product. It was built specifically to address the needs of our own internal infrastructure. But because Google Cloud Platform runs on that same infrastructure, it gets the same benefits when it comes to high performance, security, isolation, and availability. So we built Andromeda really to address the ever-increasing demands of moving traffic between storage and compute, something that traditional networking infrastructure really wasn't able to keep up with. So as you can imagine, Andromeda is also going to give us better throughput. So we have this graph here, probably a bit of an eye chart for some of you guys. On the y-axis, we have relative performance, where higher is better. And at the bottom, we have compute engine instance types, compute engine virtual machine instance types. Standard is the standard memory configuration. And then we have 1, 2, 4, and 8 cores. So these are bigger machines as we go along to the right of the x-axis. The blue bars represent the average performance, the average throughput for what we had before Andromeda, the non-Andromeda average. As you can see, this is fairly static across all 4 of those machines. The red bar represents Andromeda average, the average we see with Andromeda. As you can see with the smaller instance, the 1-core instance, we get almost double, 2x throughput performance on that particular type. When it comes to the 8-core instance, we get roughly 4x performance, 4x improvement in throughput on single-stream TCP connections. So this makes these larger instances perfectly suited for network I/O-intensive workloads, such as maybe Hadoop, HPL, any kind of application that is extremely sensitive to latency. And just to mention as well, Andromeda is our network infrastructure. It's available in all of our zones on Compute Engine, in all of our regions. And on the subject of latency, was going to be the subject of latency, I'm going to hand you over to Wes, who's going to talk to you about measuring fast.
Thanks, Mandy. So I wanted to spend a little bit of time talking around what it means to measure an application, because you guys can make all the performance improvements in the world, but if you don't know how they're impacting your application, you may be doing something bad under the covers that you need to know about. So normally when I ask a web developer, I say, hey, John, can you go tell me the performance of this particular web page or application page, homepage loading screen that's coming up? And the first number they almost always come back with, which is the easiest thing to report, is average response time. A lot of monitoring solutions report this to you. But the thing I want to point out is that this may look good. 200 milliseconds may not seem that bad. But that's only average. How do I know if 10, 20% of my customers are seeing loading times of greater than 4 seconds, and then there's a lot of people seeing really fast requests? And average response time is misleading. And that's the real point I wanted to try to make here, is that anytime you report on average, it works well when you have a model that follows a normal distribution curve. When you see things where it's like a few requests that are very fast, most of them in the middle, and then a few tailing off at the end. But the problem is that most applications don't behave like this. In fact, this is actually a more typical latency analysis curve that you would see as part of your web app or mobile application. And the reason is this behaves a little bit more like a step function, and it actually makes a lot more sense when you think about how an app is architected and built. At the very beginning of the curve, you see most of the requests. This is a good thing, and this is because most modern web applications and apps have some form of caching. So users go and hit your web server, the cache serves the request, gets the data locally, and is able to send it back to the customer really quickly. But then what happens when you have a cache miss? Well, that's when things take a little bit longer. And so if most of the users are hitting the cache, only a few of them are missing it, and this is where you start to see the decrease in the number of people that are experiencing longer latency. So as I said, it behaves a little bit more like a step function. Finally, at the end, you start seeing things that we call the long tail. This is where you need to start really paying attention to some of the stuff that's going on. This is the problematic areas that you may see, specifically this guy. If this bump right here starts to spike, it's usually indicative of a problem. It could be, your servers are overloaded with traffic and they're starting to fail. It could be a third-party API that's timing out. It really could just be a programming bug. We see a lot of examples where some user comments end up scaling out and causing really slow response times for a number of users. So oftentimes it could be a variety of these things, but you really want to start paying attention to the tail. Googler Jeff Dean sort of says this best. He goes, even if your application appears to be performing fast, always be aware of the end-to-end spectrum. Don't just look at average. Don't even look at 50th percentile. Make sure that your long latency tails are performing well. So if averages aren't the answer, what is the answer? Typically when we talk about performance, I love it when people tell me percentiles rather than averages. And to give a really quick, simple example, imagine my application got 10 requests that were served. Notice that the average of this is 102 milliseconds, but it actually doesn't say anything about how many users are seeing average response times of 102 milliseconds. And if I go and take the 50th percentile of this, I can then say, oh, well, half of my customers are experiencing latency 50 milliseconds or greater. And this gives me much more confidence in the range of users that are seeing good and bad performance on my application. So quiz time. If I was to show you guys a quick little graph of two applications that have a latency curve that looks like this, which do you think is better? I hear two, I hear one, I hear a little bit of both. You're probably sitting there saying, you just told us that averages aren't the right thing. So, of course, the answer is, it depends. And that's true. You know, in this particular example, this is actually real-world data that we took from two apps that we were running internally at Google. And we found that even though the average of app 2 was a little slower, the 95th percentile was further in. So we got really reliable, predictable, consistent performance. And it was under that 4-second magic time. You know, app 1 had some attrition rate from people that didn't want to wait for these long requests. So really, you know, the whole point of this slide is to start thinking about the range of performance across your application, and also realize that good performance engineers try to bring forward the bars. They try to move these bars a little bit left in terms of the percentile graphs. But any change that you make can have an adverse effect on the other percentiles. So always keep that in mind. You know, you might make something better for the 50th percentile, which will impact the 95th percentile. And those are just performance trade-offs that you're going to have to figure out what the right solution is for your application. So I'm going to come over here and give you guys a quick little demo. You saw some of this in the keynote today, and I just wanted to show you in a little bit more depth what was going on. We recently announced a product called CloudTrace, and I want to show you how that works. This is a tool designed to help you debug long latency tail apps. So I've loaded up the WalkShare app, and let me exit out of the comments here. It's a beautiful app that says, this is where I walk. Look how peaceful that looks. Yeah, sorry. Thank you, Mandy. And it allows you to go and comment and figure out, OK, well, this is a nice walk, or it's not a nice walk, or I've done better than that. So I'm just going to go ahead and add a test comment in here. And when I hit post, this is exhibiting some pretty long characteristics. There was a delay there. It wasn't immediate. And I noticed when I was using this that the more times I had comments on the page, the more it was lagging. And so CloudTrace is a tool designed to help you figure out what's going on there. From under the monitoring tab, you can go into the developer's console and click on traces. And this is a tool that allows you to see the requests that are coming into your application in real time. So if I was to go and filter to say, let's take a look at things in the last hour, and I can even do some searches. And then I'll sort by latency to see the slowest latency request. This was actually the recent request that I made in an earlier session. I'll go ahead and pull it up because the graph should look similar. But for every single one of these comments, the CloudTrace tool tells me how long this particular request took, and then gives me a list of the RPCs, or remote procedure calls, that were made during this request. So it's really easy for me to pull out and say, all right, well, I can obviously see the problem. I'm doing a bunch of synchronous data store calls in a loop, which is causing it to basically block on the number of comments that I have. In fact, if I even go and click on some of these other tabs, I can see that the majority of my calls are all in this data store .get method. And the fix for this is pretty simple. I ended up pulling up some code here. I'm not going to make the fix, but what I wanted to call out was I noticed that everything that I was doing here in data store was via synchronous method. We actually offer async counterparts to most of these. So I fixed the version of the app. I ended up pushing that out to production using the async APIs. And what I got was a very different picture. You can notice that most of my data store calls are now parallelized. I'm doing some puts in addition to some gets here. This greatly sped up the overall end-to-end performance of my application. And a few more notes on CloudTrace. Right now, this is a product that's in limited preview. We're going to support it for App Engine right out of the box. 0 configuration. You turn this on. You get these traces for you automatically. And as we start to roll out the lifecycle of this, we really want to extend this across not just App Engine, but Compute Engine as well, and give you guys detailed analysis on what these RPC calls are doing, what code line was calling them, and really take a deep look into what your service is doing for every single request that's coming in. Now, before I hand it back to Mandy, I wanted to impart with you guys a few little tips and tricks for how to manage long-tail latency. Tip number one, before you do anything, look to reduce the number of RPCs before optimizing your algorithms. So many times I've talked to people where the first thing they want to do is go and hunt through their code through every single n-squared algorithm and try to clean that up into some n-log-n or even fancier set of code. And that's usually not what speeds up your application the most. The number of RPC calls every single request makes is usually the #1 contributor to slow performance. And for this particular example, this is a really common thing I see where people are making a bunch of memcache or data store calls, and they don't realize that you can actually batch these together. Data store provides really nice mechanisms for retrieving data via a batch operation where you're able to pass in a set of keys as opposed to each one individually. Tip number 2. Cache read-only third-party API calls. The thing to remember is that if you're making a bunch of calls up to Facebook, Twitter, Google Maps, whatever, they have the same performance characteristics that your application has as well. So realize that for every 100 calls you make, 99% of them are going to be very fast, but there is a chance that a few of them are going to return very slowly. They could either time out or they could just take a long time to return to you because they have the same latency curves just like you do. Even worse, if you start to load a page that chains a bunch of these together, say like an account details page that wants to show name, address, billing information from all these different services, you're increasing the percentage chance that one of these services is going to return slow. And if your page happens to block on showing that information, well, then you end up in a little bit of the problem. So the tip here, when you can, if you have some data that is not likely to change very often, is read-only, cache that locally. Name and address are really good examples where you don't necessarily need to make API calls for all of that stuff. Store it locally, make the retrieval faster, and try to reduce the number of external dependencies your application has. And then the last one, this is sort of a no-brainer, but I like to remind people because not everyone realizes that we have asynchronous methods for almost every single one of our outgoing calls in App Engine. The synchronous methods have an async counterpart. So really learn the documentation, be aggressive about using the async, put in a pretty aggressive deadline limit. You can actually specify how long to wait before a particular RPC call is returned. You can be a lot more aggressive in sending out a few of those just in case one of them happens to return slowly. And with that, Mandy's going to talk to you guys about, once you have everything up and running, scaling out fast so that your application can handle a lot of load.
Thanks, Wes. So what do you do when you have to scale for a one-off global event involving one of the biggest social media entities on the planet? Okay. How many of you have heard of One Direction? Come on. How many of you have heard of One Direction? All right. There wasn't many hands up, and I think most of you are liars. You've all heard of One Direction. You just want to admit it. Right. So back in October of last year, we received a request from our marketing team to assist an agency with the development of a second screen application for what was known as One Direction Day. And One Direction Day was a 7-hour continuous YouTube live stream by the boy band One Direction. And we were told in October, the event was on the 23rd of November, that it wasn't a huge amount of time to get this done. Also, scale was a particular concern because based on previous live streams that they had done with the band, they estimated a potential concurrent usage of 650,000 concurrent users. So because of the two factors, the short amount of time involved, and also because of the scale involved, the agency chose to use Google App Engine. So this is what they built, very simply. The user would connect to the App Engine application and would be asked to log in using Google Plus Sign-In. Once they logged in, they would be presented with questions. New questions will be available every 10 minutes, 6 questions every hour, 42 questions in total, and there's absolutely no significance in that number, 42. So they were presented with questions every 10 minutes, and they would answer the question. The client-side code would return the answer to an endpoint running in the same application, an endpoint that was designed to handle all of our data services. And that data about, well, any correct answers, only correct answers, were stored into Memcache, along with any demographic information that we have that the user had allowed us to actually gain from the Google Plus sign-in. Now, we stored it into Memcache, but because this was a one-off event, we didn't actually store it through to our backend store. So this wasn't a write-through cache. This was just stored into cache. Now, App Engine has a shared Memcache service. A service is completely free that's shared across all applications running on App Engine. Obviously, that would make it a little bit volatile. So we had this feature as well in App Engine called dedicated Memcache, which is what we use for this, this event. We reserved about 20 gigabytes of space in Memcache, specifically for our application. So all of the data was stored into Memcache, and there was another endpoint that's not shown on the diagram that was used by the organizers of the event to query that data that was stored in Memcache. And that allowed them to come up with interesting statistics, such as 95% of people in the age range 20 to 30 in Brazil answered the last question correctly. They could then put that data on tickers at the bottom of the live stream and broadcast it live. After the 42 questions have been delivered, we would drain the data. After the event is finished, the data will be drained out of Memcache into Cloud SQL, which is our MySQL in the cloud offering. That's the application. That's how complicated it was, or not complicated. So obviously, scale was a big concern, and we, in partnership with the agency, did some load testing before the event, did lots of load testing before the event, up to 10,000 queries per second. And queries per second are what we use internally in Google. Generally equates to requests per second. And that was great, 10K queries per second. The URL of the application was leaked before the event, so we were able to see a steady ramp up in traffic. It was leaked through social media, so that ramp up was relatively exponential. But it did allow us to test some assumptions and also to fix a couple of issues that we saw with our API quota around Google+. We didn't leak the URL, but if I was ever going to do this again, I would definitely leak the URL myself, just to make that happen, because it was great. Then we settled into this steady traffic pattern, where we saw every 5 minutes a peak of about 600 and a peak of about 700 queries per second. That's what this graph shows here. Now, we had to try and avoid the issue where potentially 650,000 users would all answer a question simultaneously. So the delivery of the questions, or the availability of the questions, was staggered over a period of time. And that's why we have 2 spikes, and why the spikes are reasonably broad. So that went on for about 4 hours, and about 4 hours into the event, the organizers of the live stream decided to announce the application live on the event. And that gave us this spike here, slightly different x-axis here. We saw a spike of 9,000 QPS. And later on, we saw a spike of around 5 or 6K as well. So that was fine. We'd tested up to 10,000 queries per second. We had capacity to go way beyond that as well. So that was fine. We had no problems with that at all. And we had no problems with this because App Engine just scales inherently. There's not a huge amount a developer has to do to actually scale on App Engine. Obviously, with an event of this size where we have to scale massively and rapidly, there are certain things we have to do within the application to make sure it doesn't bottleneck or anything like that. But generally, if you're building an App Engine, you'll just scale. The instances, it's very small micro virtual machines, are spun up very quickly, torn down very quickly. So you always have what you need when you need it, but you only pay for what you use. But how do you scale Compute Engine virtual machines? So Compute Engine is our infrastructure as a service offering, where App Engine was our platform as a service offering. And we're trying to blur the lines between infrastructure and platform. So how would you go about scaling Compute Engine virtual machines? So you do it this way. This is something that we announced back in March of this year. We announced Deployment Manager, replica pools, another thing called resource views, which we're not going to talk about too much today. They're a little bit obscure. But basically, we like doing things in Google declaratively. We like creating templates or config files and building stuff from those templates and config files. So this is an example template. It's not really there for you to read, but this is an example of a template. That will be fed into a service called Replica Pool. And Replica Pool would do all of the work in converting that template into a deployment, which would look something like that. So this is a group of virtual machines. These are what Chris Ramsdale would call a fleet of homogeneous virtual machines. And they're all the same. They're all identical. They're all built from this template. There's no snowflake servers here. And we have a load balancer as well configured to distribute the load across the pool of virtual machines with a single endpoint, a single IP address you can connect to. So for all intents and purposes, they look like one virtual machine, but there's many. Replica Pool also offers a monitoring service as well. So it can monitor the health of these virtual machines, and if they break, they can bring them back up again. This is all done through an agent running on the virtual machine. Okay, so that's a replica pool. This is a static resource. We can scale it manually. We can add replicas. We can remove replicas and size the pool manually. But how would we manage autoscale in this situation? So now we're going to talk about something called Autoscaler. Autoscaler is already available as part of Deployment Manager. Ultimately, it will be made available as a separate API. But Autoscaler allows you to create a config within your template that sets up autoscale parameters. At the moment, the only thing we can autoscale on, and this will change, the only thing we can autoscale on is average CPU utilization across the entire pool. And that's what you'll see there where it says target utilization 0.5. That's effectively 50% target, 50% CPU utilization averaged across the entire pool. So whenever we go above 50% utilization on average, we'll spin up new instances. Whenever we go below 50%, if we have too many instances, we'll turn them down. That's how autoscale works. And now we're going to give you a demo of that actually working. So this is the kind of demo you can spend 30 minutes on. So I'm going to try and do it in 3. Can everybody read that? Can everybody read it? Yeah? No no's? Okay, good. I should have asked if anybody couldn't read it. Okay, so back to my slide just briefly. I just wanted to set that up. So I'm going to go through the left-hand side of what this demo looks like, and then I'll go through the right-hand side once I've kicked it off. It takes a little bit of time to run. So we're going to be making use of Google Cloud Storage. Google Cloud Storage is an object store. It's a bucket-based store for unstructured data. It has a lot of really nifty, sorry, that's a British term, a lot of really cool features. A lot of really cool features that you can make use of. One of them, the one we're going to make use of, is called object notifications. So we have these buckets. We have an input bucket and an output bucket. So what we're going to do here is solve a relatively complex problem whereby a user has a large number of images coming from some source that she wants to convert into thumbnails. And she wants to do this very quickly. We don't know why she wants to do it very quickly, but she needs to do it very quickly. So that's the problem we're going to solve here. So we have an input bucket, which will receive incoming images, and an output bucket, which will receive thumbnails. So having said that, I'm going to kick the actual copying over of images off now while I talk. So Cloud Storage has this tool called gsutil, and it allows us to copy files from one bucket to another. So in this case, I have a bucket that's pre-configured with about 1,111, exactly 1,111 images, which I'm going to copy over from that bucket to another bucket. So the first thing we need to do here, though, is look at what we have to begin with. So if I go to the developers console, which Wes showed you earlier, this is my replica pool, which I created before. I've actually set this replica pool up with a load balancer with one virtual machine. And this is the virtual machine, IO14 demo Y598. That's all we have. You can see from the spikes on the graph that I have been practicing this demo many, many times over the last few days, which is quite fun. And it's always worked. So hopefully today it's going to work as well. So what else do we have? We have cloud storage. Now look at cloud storage. We have 3 buckets. We have our images bucket, which is where the input images are going to come into. And we have the thumbnails bucket, which is where the thumbnails will be written to. Then we have the payload bucket. And this is where all of the images are. So this could be any source. This could be some source of images, a stream of images, a batch of images, but we're basically going to copy them over from one bucket to another. So gsutil allows us to do that. It allows us to copy from one bucket to another. So we're going to copy from autoscale-io-payload all of the files into autoscale-io-images. And we're going to do this in parallel. we're not going to pull the files down and then push them back up. It's just going to copy them between the cloud storage buckets directly, right? Internal Google infrastructure. And we're going to do it in parallel. Because for some reason, this always seems to fail, I'm going to do this first. ulimit minus n 10,000. That allows me to have 10,000 file handles. And for some reason, that seems to reset itself every now and again. I have no idea why. Now we kick off the copy, and that will happen in the background while I continue talking. Is it more interesting to watch this or to listen to me talking? I'm not sure. OK, so going back to the slides, what we have here is object notifications. So object notifications are really cool. Whenever anything is added to the bucket or anything is updated within the bucket, any object, a notification will be fired. And that notification will be in the form of a URL that's being called by the notification. Now, so every image we add to the bucket, we're going to have one of these calls specifically for that image to a URL, which we've registered ahead of time. Now, that URL could be a load-balanced pool of replicas, a load-balanced pool of virtual machines. But that gives us no control over the way in which data flows into the system. So we're going to use something in App Engine. We're going to use an App Engine application and something called task queues. How many of you have heard of task queues? See, task queues are one of the best features of App Engine. They allow us to actually do work outside of the user request. So the request deadline for a user request is 60 seconds. Often you want to do work outside of that, so you'll use a task queue. And what you do is you create a task, you put it onto a queue. And then you have something in App Engine consuming those tasks from the queue at a rate of, by default, 5 every second. The application that's consuming those tasks will process the request and then create a request, another HTTP request, to our pool of load-balanced virtual machines. And this will be distributed across our virtual machines, hopefully in a round-robin style, across all of them. We only have one to begin with, so there's not much to distribute. But hopefully we'll have more before the end of the demo. Then we have a process running on the virtual machines that will process the images with ImageMagick and create a thumbnail. So we go back to the developers console, look at that. First thing we will look at is the thumbnails bucket. And hopefully when I click on this, we'll see a whole bunch of thumbnails, which weren't there before. So these are the thumbnails. The thumbnails are a picture of me, because I'm an egotist, or something like that. So we're getting thumbnails. That's good. We want to get thumbnails. What about these virtual machines, though? How many do we have? We have 2 currently. So we've doubled the size of our pool. We've added another virtual machine to do processing. So this basically is set up to a threshold of 0.3, which is 30%. So we're looking for 30% CPU utilization. The application running on the virtual machines is a Go application, and it's using Go routines, so it can do the request processing in parallel. Normally we get 4 virtual machines. Today we've only got 2. It really depends on how quickly we can pull that data down, suck it down from one bucket to another. So let's see what happens and see if we get any more. So now we've got 4 virtual machines. So now what we're going to do is go back to the slides and look at one I created earlier in real Julia Child style, as Julia would tell me. And we have this graph, which shows you CPU utilization, the blue bar, against number of virtual machines. Now, obviously, this wasn't for this one. This is a run I did on Saturday. And you can see that as we hit 30% threshold, we spin up a new virtual machine. We spin up more virtual machines. The CPU utilizations come down. At some point, we say we have too many virtual machines, so we remove them. Obviously, you don't want that to keep happening bang, 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 bang. So you have this cooldown period where you can say there has to be a minimum of this time between requests, or between autoscale activations. And that's what happens. That's the demo. We'll come back to it later if we have time. So I just want to share a couple of tips with you, as Wes did with measuring fast, a few tips on scaling fast. So the first one is always to use Google App Engine as the entry point for your web applications and as the API service for your mobile and gaming backends. As we've seen with the example of One Direction Day, App Engine scales extremely well and extremely quickly. And there's very, very little work on your part that you have to do. Now, some applications aren't best suited for App Engine, and in that case, you can use modules, build a modular application where all of your front-side stuff is on App Engine, but managed virtual machines being managed by App Engine are running your back-end code. That's really easy and simple to set up. Also make use of edge caching. So we've seen that with Andromeda, we have much higher throughput, particularly on larger instances, but throughput always involves latency. So any kind of movement of stuff through the network will involve latency. So the best thing to do is cache your content as close to the user as possible. And you can make use of edge caching, which is caching in our data centers or with ISPs, because we have a global peering relationship with many ISPs. And you can do this with App Engine using static content, with cloud storage by setting cache control headers on any data you store. And with App Engine, again, you can do it on dynamically generated content by setting cache control headers on the response stream. And very quickly, because we're running out of time, I'm going to run through these very quick. The network I/O intensive workloads make use of those big virtual machines for more network throughput. For scaling, App Engine can sometimes do with some help for scaling, and you can use idle instances on App Engine to make it scale that little bit better. Idle instances effectively answer requests when there's no instance available to actually answer that request immediately. So they're there really as a backup to answer requests. And the final one is to take advantage of features such as page speed and memcache. Page speed effectively is an App Engine application or an App Engine service that's free to anybody who has a paid application, have set billing up on their application. And it will optimize your HTTP requests. It will compress and cache data. And it provides services such as inlining and critical path rendering. Memcache, you guys all know how to use Memcache, but you can also take advantage of dedicated Memcache, as we did with One Direction Day. So we've seen that Google is built on a culture of fast, and that we're constantly driving innovation within our infrastructure in order to maintain and improve performance across all of our APIs and services. We've also seen the Google Cloud Platform benefits from this innovation through network stuff like Andromeda. Sorry, I forgot what I was going to say then. We've also seen that long-tail latency is an issue, and it can be addressed with the ability to measure fast, as Wes showed you. And we looked at tools such as CloudTrace that allow you to actually gain rapid insight into issues, that kind of issue running in applications in the cloud. And finally, fast matters. We come back to the message that Wes had initially. Fast matters, fast will always matter, and Google Cloud Platform can help you build applications that run fast in the cloud. So what are you going to build? With that, we're going to sign off. We've only got a couple of minutes of questions. The call to action, go to the Cloud Platform blog and find out about features that Wes talked about and that I talked about. Preview features such as Deployment Manager and Replica Pools, you can sign up there. The next session is in room 7, Zero to Hero with Google Cloud Platform with Chris Ramsdale. You can provide feedback via the QR code. There's one up there on the board. And you probably haven't received anything about this yet, but you can get $500 in credits for the Google Cloud Platform. Go to g.co/cloudstarterpack and enter the promo code Google.io. And there's also a roadshow in the US happening very soon. And you can go to googlecloudroadshow.com to sign up for that.
Great. And if you guys have any questions, Mandy and I are going to be sitting outside in the cloud booth over there. So come find us. Thank you very much.
Hi, I'm Brad, the lead engineer on our new in-browser native client development environment. I'm going to demonstrate how easy it is to use that environment to check out, edit, build, and debug a C++ application all in your desktop web browser or on a Chromebook. Also, with this environment, you can even work while offline. Visit this page to follow along. You'll need to install our new tools. I've already done that, so I'll go ahead and fire up the new dev environment. It looks a lot like a Unix command line bash prompt, because it is, running inside the secure native client sandbox. So what you do in this environment stays in this environment. Let me create a work directory. Our new environment works like its own mini Unix system. Files you create are retained in local web storage, securely separate from your computer's main file system. I'll download a zip file containing my project using a command line program called curl. Once I have my project, I no longer need network access and can work offline if I like. Here's my zip file. I'll extract it. Let's look at what we got. My project uses a bunch of different programming languages. The core application is in a C++ file called Voronoi CC, which is combined with several C++ libraries. These are then built with Knackle's GCC-based compiler, yielding a Knackle executable, Voronoi Nexi, all of which is driven by a bash build script. Voronoi Nexi is then combined with some HTML and some JavaScript, which creates a Knackle DOM element and routes UI actions to Voronoi Nexi, yielding the complete web app, which is then served up locally by a Python script, once again running in the Knackle sandbox. Before we get going, I'd like to track my changes, so let's create a Git repository. Then add all the files here. Now I'll commit the starting state. Great, now let's build. Oh, that isn't right. It isn't building at the moment. Looks like the problem is on line 506. Let's open it up in Vim. We have a port of Vim to native client, but fear not, Emacs users, Emacs is coming soon too. The problem was on line 506. Let's go check it out. There's the problem. I've misspelled height. I'll fix it. Then save. Compile again. Victory. I can look at the diff using Git. I should really commit that fix. Now I'll fire up a local Python test server using our Knackle Sandbox Python and navigate to my test page. The Python server lets me view my entire virtual file system. In the /mount directory is an HTML5 local storage mount, which is where my home directory lives. Let's go into the work directory we created before. Then we can navigate to the Voronoi directory, which will load our app because it has an index.html page. Here's the sample running just on the main thread. Kind of slow. Let's crank it up to 32 threads and use all our cores. Uh-oh, it stopped. No worries, let's debug it using Knackle's new in-browser GDB-based debugger. I simply open the developer console and select the Knackle debugger tab. Our port of GDB allows you to attach to a running application, but will also automatically connect to a crashing one. GDB allows us to inspect the state of each thread, including local variables and call frame, to help us track down bugs in C and C++ applications. Let's get a stack trace. Bad things happened at line 485 in Voronoi CC. Let's go back to Vim and check it out. I see it. Do you? I botched value. Spelling is clearly not my strong area. Let me fix it. Save. Rebuild. Double check the diff. Let's commit that too. Let's look at my commit history as well. There are all my changes. Let's give this new version a go. Works like before. Now let's add some more points. That's really janky slow. Let's try our 32 threads again. much better. Use Native Client and our new development tools to bring high-performance applications to the web, whether your application is written in C, C++, Python, Lua, or Ruby, with more languages and portable NACL support coming soon. Try this tutorial at the link above or visit our developer site for more information on how to use Native Client to supercharge the web. Thanks for watching.
Speed matters for applications. You could be doing intense image processing, complex scientific computing, or just delighting users with an immersive game. Portable Native Client brings speed to the web. I'm JF, lead engineer on portable code performance, and I'm going to walk you through how Pinnacle delivers the speed your users demand and you deserve. Going faster allows us for better games, makes users wait less when they interact with applications, and reduces the amount of energy used by the device. And as we all know, longer battery life means more game playtime and happier users. Modern processors have a treasure trove of performance that often goes unused. Let's explore a few kinds of parallelism that unlock this performance. One source of parallelism is at the task level, where independent work is conducted in parallel on multiple cores. This is achieved in Pinnacle through POSIX threads, which have been available since launch. Another type of parallelism is at the instruction level. Modern CPUs fetch an instruction stream and decode, reorder, schedule, and execute instructions using a plethora of functional units, all in a very deep pipeline. This parallelism allows the CPU to execute multiple different instructions at the same time and is mostly free for programmers. Typically, this has been the realm of compiler engineers, but it turns out that those functional units are just there waiting to do something, and some of them are pretty powerful, yet usually go unused. If you don't use them, then your CPU isn't showcasing its full power. It's leaking power instead, trickling in small amounts of work instead of going to sleep. Let's zoom into one of the previously mentioned functional units. Programming languages typically expose scalar instructions, shown here as a stream of 4 instructions. The CPU loads one input datum per instruction and then executes one instruction to generate one output datum per instruction. This is a scalar way to do computation, which gets the job done, but it doesn't fully use a CPU's capabilities. CPUs have more than just load, store, and scalar functional units. And that's where data parallelism comes in, where the functional unit takes instructions and performs the same work on multiple sources of data per instruction, generating multiple output data per instruction. This single instruction multiple data model is called SIMD. There's still a single instruction stream, but multiple pieces of data are fetched at the same time, operated on, and multiple corresponding outputs are created. The SIMD functional unit can perform 2, 4, 8, 16 or more operations in a single instruction. Let's look at some code. SIMD is usually expressed through architecture-specific assembly code or intrinsics, SSC and AVX on x86, and Neon on ARM. Pinnacle expresses SIMD using portable intrinsics that are very similar to those used on x86 and ARM, and those intrinsics lower to efficient code for each target architecture. You can see a great example of Pinnacle in action by taking a look at Google Plus Photos editor. The team took existing photo filtering software written in C++ and were able to use it directly in the browser. Photo filtering typically uses many forms of parallelism, including SIMD, and they operate very fast on large images by using fairly complex imaging pipelines, most of which are inscrutably complicated to me. But hey, they work and they're fast. Those complex pipelines deliver beautiful results and allow users to add some magical elements to their pictures. Using portable SIMD intrinsics was minimal effort on the photo team's part because some of their filters use a language called Halide, an open source language developed at MIT, which simplifies image processing by decoupling the algorithm from its schedule. Sometimes it's more efficient to compute images breadth first. Sometimes it's better to fuse value computations, use sliding windows or tiles, or even a mix of techniques. SIMD plays a small but critical part in using all of the CPU's capabilities, and Halide's biggest strength is in expressing image processing algorithms and mapping them very efficiently onto the underlying machine, as shown here. Applications which are suited to Halide's computational model should definitely consider using it. Here's another usage of SIMD as well as threads on the web. Folding at Home does protein folding for medical research to help cure diseases like Parkinson's, Alzheimer's, and cancer.
Protein folding is incredibly complex, and the research greatly benefits from the web's huge reach. Merely using Pinnacle over the usual web platform increases performance by 2 to 4x. Using threads is a multiple that's roughly linear in the number of CPU cores, and using SIMD is yet another 2 to 4x. The Chrome browser enables these great speedups through Pinnacle with technologies like threading and intrinsics. That doesn't mean that your development process on other browsers have to suffer, though. Pinnacle offers a powerful toolchain based on LLVM, and we support generating Pinnacle executables as well as JavaScript ones, so you can fold proteins in all browsers. This is done through Pepper.js, which relies on Emscripten. While this fallback comes with some caveats, we strongly believe in evolutionary improvements to the web platform as well as revolutionary ones, such as what I've just presented. This completes our brief tour of some of the latest performance improvements we've brought to Pinnacle. SIMD will be available in Pinnacle as part of Chrome 37 to be released at the end of August. For more, check out our site, gonacl.com. We're just getting started with performance improvements to the Pinnacle platform. On the SIMD side, performance will improve significantly over the next few releases, and we'll add powerful new intrinsics as well as fun features like auto-vectorization. It's now your turn to use all this power on the web. Thank you.
Hi everyone, my name's Max and I'm an engineer on the Chrome team. Today I'd like to show you my favorite way to build amazing Android and iOS applications. Using web technologies, you can install Chrome apps on mobile devices. First though, a bit of background. Many of you are aware that you can build applications for Android and iOS that heavily leverage the WebView component, to the extent that your application is almost entirely built with HTML, JavaScript, and CSS. Now, to be clear, these are apps that you still install from the App Store. They have an icon on the home screen and full access to device capabilities like any other app, but they're built using web technologies. We often call these types of applications hybrid, because they're a blend of web and native technologies. On Android, one drawback of hybrid applications is that web views on older versions of Android can be a bit limited. Chrome has seen a ton of improvements on Android, especially over the past year, but running on old web views means that you can't take advantage of those improvements. That's where the Intel Crosswalk open source project comes in. The Crosswalk project provides an embeddable Chromium web view for Android versions as far back as Ice Cream Sandwich. Using Crosswalk, hybrid applications can run on the latest version of Chromium, regardless of Android version. Similarly, on iOS, the web view has seen great updates since version 6, and now with iOS 8, the web view will match the full capabilities of the Safari browser. Now, what does this all mean? Well, it means that it's finally possible to build hybrid apps that use a modern web view and run on almost every Android and iOS device released within the past 3 years. Now, here's an HTML5 canvas-based game called Pop Pop Win, running on the Crosswalk web view. Smooth as silk thanks to a hardware-accelerated canvas. This wasn't possible a year ago. Nowadays, hybrid apps can use technologies like WebGL, WebRTC, WebAudio, accelerated 2D canvas, and modern web toolkits like Polymer, all at maximum performance without the need for browser polyfills. And it gets even better. Hybrid applications are not limited to just using web APIs. Since these apps are also native apps, you have full access to all Android and iOS device APIs, such as identity, cloud messaging, notifications, payments, Bluetooth, sockets, cameras, and much more. Here's an app written using Polymer, showing off some nice animations running polyfill free. So it's clear that there's a lot to like about hybrid app development. But how do you get started? Well, over a year ago, our team started contributing to the popular open source hybrid application toolkit, Apache Cordova. We also took a look at the amazing work being done with Chrome packaged apps for desktop. So, in January, we released a developer preview of a tool called CCA, which allows you to build hybrid mobile apps using the Chrome packaged app format. Now, one of the most convenient aspects of web development is its extremely rapid workflow and short feedback loop. No compiling. You can just make a change and see it right away. Sadly, with hybrid apps, like all native apps, you do have to wait for compilation, so you lose that rapid feedback loop. Our companion tool, the Chrome App Developer Tool for mobile, changes everything. Let me show you how it works.
Ready to rock. Hello! Are you enjoying Google I/O? Whoa, that's great! Let's hear it again because I'm going to involve you in this session. Are you enjoying Google I/O? Fantastic. I am enjoying Google I/O a lot. This morning when I woke up, it felt like Christmas, you know? But then I thought, I'm going to work today, so it's not really Christmas, but I don't work at Christmas. And then I thought, I wonder what Santa Claus staff is feeling on Christmas when they are working. That was a really weird thought, so I stopped that. We're going to talk today about Google Play Services. And probably many of you in here know what Google Play Services is, but I will do a mandatory recap for you because there may be some people in here that don't know what Google Play Services is. Google Play Services is a set of APIs that we develop in Google and deploy on Android devices running Gingerbread or later that has Google Play installed. And that's a lot of devices out there. There's just a small percentage or two or so of devices that runs Google Play that is not included in this set. So it's a vast majority of the Google Play devices. Oh. It's unfortunate that you can terminate the presentation with the clicker, right? And the good thing with Google Play Services is that we release it many times every year. So there are multiple releases being pushed to all of these devices per year. Now, if you're still thinking, so what's the big deal about that? Then I will tell you it's a huge deal. It has monumental value, right? Because this allows Google to get the latest and coolest and most shiny stuff that we develop in mobile technology to get that out to developers quickly. Are you developers? Yeah! That's great. And that stuff that you develop on Google Play Services API can be used on almost all the Google Play devices out there. That's great, isn't it? If we look historically, we've been releasing 12 Google Play Services versions since we started with this back in September 2012. And I'm happy to announce that right as we speak here, we have a 5.0 being pushed out to the world. And you will actually get a sneak preview of this version as well. So more information on that is coming later. But it's going to be great stuff. Some of that stuff I will present here today. So stay tuned. I love Google Play Services because of this, because it has all of these capabilities that you can build into applications, right? You have location with GPS, you got the maps, the wallet API, you got play game services, mobile ads, social with Google+, Chromecast, the Google Cast SDK, Drive, and Cloud. It's absolutely amazing. You can build so many cool applications with all of these APIs.
Tell them that Google Play Services rocks.
Yes, that's exactly what I'm going to tell you now. Google Play Services rocks. It really, really rocks, right? And we're going to do a little exercise here. I brought the T-shirt launcher with me. It looks like this, right? And this is probably what's going to happen. At various locations of this presentation, I will go crazy and put my arms in the air, and I will say, Google Play Services. And then I expect from you, yeah, exactly. Exactly. Let's try that out once. So, okay, Google Play Services. Whoa! Great stuff. A little reloading there. I can just see this later. Weird guy at Google I/O launches t-shirts at audience. Asks for rocks in return. All right, let's get started, shall we? Ladies and gentlemen, let's introduce a new API to Google Play Services, namely the Android Wear Data API, with a round of applause. Here we go. You've seen Android wearables being launched at the keynote today, and this is big stuff, right? It's the first time I'm wearing something around my wrist for the past 15 years, right? I've been taking my phone up and down this pocket. I think in the keynote today there was a note that 100 billion times this happens every day in the world. It's amazing, isn't it? I have tear marks on my left pocket here because I'm reaching for the phone so often. Well, those tear marks I will not need to have anymore because I got all of that information right here on my wrist. It's absolutely amazing. And Google Play Services obviously has an API to integrate with these wearable devices because you need to transfer things between these devices and communicate across them. And there are 3 APIs that we are launching as part of Google Play Services in the Android Wear Data API. The first part is the Message API. The Message API allows you to send unidirectional messages between the wearable and the phone or tablet, or the phone tablet to the wearable. These can be control signals. For example, you can tell the wearable to change the media track that is playing on your Android phone. Or you can have your Android phone instruct the wearable to launch an intent that gets visible to the user. So that's a great API to share information between the phone, the device you have in the pocket, and the wearable device. The second API is the Asset API. The Asset API you use to transfer binary blobs, images, for example, or other kinds of binary data between the wearable and the other device. So this can, for example, be an image. One use case would be your phone downloads an image to the phone, right? It resizes it to match the resolution of the wearable device, and it then sends it over to the wearable device as an asset. That's a perfect example of data being transferred as an asset. Then we have Data Item. Data Item is an API is a message exchange in this API that allows you to have data which is in sync on both the wearable device and on both the wearable as well as the other device, such as the phone. That means that if it changes on one side, it will be automatically synced on the other side. So that's also a great API. So this is really fabulous, right? What applications will we see here in a couple of weeks? I'm really, really excited about this. And as I said, the 5.0 release of Google Play Services, we're giving you a sneak preview of that. So you'll have a running or flying start when you start to check this out. It's really, really great stuff. So I think that this demonstrates that Google Play Services. Yes, it does. Whoa. It rocks, right? It rocks. Whoa. Wow. Okay, let's move on. For wearables, we have a number of different I/O sessions here, right? So this is a list of them. You should definitely go and check them out. There are so many resources that you can consult during these 2 days regarding wearable technology. Let's talk about the buying experience, right? I love to buy things. Buying on mobile is not very simple, or hasn't been at least. There are 3 components that makes it quite complex: the identity component, the payment component, and the data entry. Now, we worked on the identity and payment for a long time with sign-in with Google+, right? And Wallet has been around for a while too. So you have Google Wallet to pay for things. But the problem has been also the data entry. I mean, when you're a mobile device, it kind of looks like this, right? Big fingers on small keys. How am I supposed to enter my address using these keys? That's impossible, right? I can barely remember my address, right? Let alone enter it on these types of keys. I've seen people do it. I mean, you've seen teenagers, they're like, two hands, multiple fingers being used simultaneously, both hands, right? Completely impossible. I can't do it. Lately, I have started to using this kind of swiping moment, you know, where you can swipe the characters and they form a word. It's really cool. I feel cool when I do it also. I will be home at 6 p.m. Right? It's really, really cool. I love it. Well, the problem is that it's not easy to enter an address with these kind of method either. So we're happy that we've released the Address API recently in Google Play Services. Ladies and gentlemen, you can now sit in the comfort of your best keyboard, enter as many addresses as you want, right? And they get recorded with the Address API. An application can, they say, where do you want to ship this thing? It can then ask the Address API. The Address API will ask you to give permission to the application to have the address. And voila, the application will get the address. Not a single press on any key, right? It's just a user interface to select which entry of that list that you want to have. Isn't that great? I think this is fantastic. This is a perfect feature for me, at least. Another feature that we're adding in 5.0 is the OCR scanning of credit cards. So as you can see here, you can now press on the camera button. When you want your credit card to be scanned, you can just align your card with this frame here, and the card number will be automatically provided to this registration of the new card. That's also cool, right? Because how many remember their credit card numbers? You're sitting there like, It doesn't work. So that's a great addition as well. Wallet fragments. It is now super easy to add the Buy with Google button to your application. We've reduced this to be a very, very small, a minimum amount of code that you need to use in order to add this kind of stuff to your application. So we hope to see lots more developers to embrace this as well. And we did a little demo here that I pre-recorded for safety reasons. And what we're going to see here is me going into a site. I have never been to this site before, right? Me going into this site for the first time, registering, logging onto the site, buying a bike, getting it shipped to my home address. And all of that will happen in less than 10 seconds. So here we go. So I log in with the Sign In by Google button. I select my account that I want to use. I come in, I select the adjustable bike that I want to buy because it's cool. I'm buying it with Google. I confirm the order and the shipping address. Voila, 10 seconds, and we've just bought the bike. Isn't that amazing? Yeah. I think that's great. All right, we're at that point. My gosh, in that case, we need to do this. I think that demonstrates that Google Play Services. Yes. Whoa. You want to have another one? Yeah, I got plenty of these. Over there. Whoa, that was... Great. Let's move over to the selling experience, right? Because you can't have a buyer unless you have a seller, right? So they're kind of mutual dependent, even though it doesn't sound as good to be selling things for some reason, I don't know. This is a picture of my wallet. This is a very important topic for me. I want to try to keep my wallet as small as I possibly can, right? I'm down to below an inch, something like that. If I was to accept every single loyalty program or coupon or whatever I am offered in my stores that I visit, this wallet would probably be 10 inches thick, right? It would be like that. If I was to sit down with that kind of wallet, I would kind of be tilting to the side, right? Because I would have this wallet which built up on one side, right? I would have to do a customized pocket to be able to get that wallet into my pants. Well, that, ladies and gentlemen, is not needed anymore, because now we're introducing to Wallet the Save to Google button. So let's welcome the Save to Google button with a round of applause. get back to work. That's right, let's get back to work. The Save Card to Google allows you to store loyalty cards, but not only loyalty cards, also coupons and discounts and bonuses and all other kinds of stuff. Allows you to store that stuff in Google Wallet, right? And then your applications that you can create, you can add this button to your application so merchants that you are interacting with can store their stuff to Google Wallet. That's great, right? It requires no more physical space, all of these things. And if we tie that together with context and location, for example, if I'm walking into a store, right, then that store can offer me things based on what my loyalty program is, my status is, and also it can utilize the coupons that I've collected. Because how many of you are carrying around all the different coupons that you are being offered in stores, right? It doesn't happen. This needs to happen if we're going to have a pleasant buying experience in the future, not to mention the selling experience, right? And this was actually one of our partners, Belly, that did an early integration of this, so we're very happy for that. This functionality will keep the merchants happy, of course. They can offer the things. They don't have to stand there with a customer that refuses to take a card because they don't have space in the wallet. It will keep the customers happy because they will get better offers and better rewards, right? And it will keep you developers happy because you're connecting the dots between the selling endpoint and the buying endpoint in this particular case. It's a win-win-win. It's the best value proposition that you can create. Perfect alignment between all the parties, right? It's amazing. Another piece that we've added to Google Play services to make the selling experience better is Google Analytics. Now, this was added in March 2014, but it existed as a standalone library before that. Google Analytics allows you to measure, this is going to sound terrible, but this is actually true, I think, allows you to measure what is most important to you, right? And what does that mean? It means that you can put things in your application that will get reported as statistical information. And later on, you can see how your application behaves, how your users are interacting with it, how they are discovering it, downloading it, installing it, under which conditions they're upgrading to a paid version as opposed to a free one, when they're doing in-app purchases, etc. There's tons of material here in Google Analytics that you can use in order to improve your app experience. And that's pretty good because it will make your users happy, right? You will provide an application that makes sense to them. And it can be good for you because you can drive more revenue through your app as well. So that's great stuff. Google Analytics. As part of 5.0, we've added enhanced e-commerce to Google Analytics. And this provides even a more detailed level of reporting. So now you can dice and slice your data that you get all the way down to the product level, right? So you can see during the purchasing process when a user is going through adding to cart, etc., and checking out, you can see what they're doing with that product before they're deciding to buy it. For example, how many users wants to do the detailed product page before they're buying the product? Is that relevant for my product to be sold, that there is a product detail page or not? So lots of stuff that can be done here. And e-commerce, as you know, is an area that's exploding in terms of growth, tremendous amount of growth. So this is a great addition to Google Analytics. Let's move over to mobile ads. What we did previously in Google Play Services, just recently, was we added in-app purchase ads. This allows users to, in the device, directly purchase virtual goods that are advertised. And it also allows the ads to be targeted to different user segments. So depending on who you are, you may get different ads. And in 5.0, we also made this extremely easy by providing APIs that allows you to configure this in a good way. That's great stuff. Don't you think that this demonstrates that? Yeah. Google Play Services. Yes, I hope it works. Whoa. Sorry. Whoa, that's better. All right. there is an I/O session on Wallet as well that you should check out. The instant buy everywhere that's taking place. Really great stuff on Wallet. Play game services. Who likes to play games? One or two? Oh. I love games, right? I love, especially I like zombie games for some reason that I haven't figured out. But okay, in games we've done a lot of different stuff, right? We've added multiplayer recently. Achievements is now a part of games. And leaderboards. You can see, if you see the evolution of requirements, things that we've added to games, that we're really creating a great platform to build games upon. All the things that you want to have, that you have to build yourself before, is pretty much becoming part of this platform. One thing we added just recently is the Game Gifts API, which allows a user to request a gift, a wish, to send a wish request, to request a gift, right? So this could be a virtual life or something where you run out of life. And another player can send a gift request to give something to the other player. And that, of course, will make the first player very, very happy. Now, happy players are great, and if they're collaborating to become happy, that's even better because that increases the social engagement between the players in games. Pretty perfect, I think. In 5.0, if we look at 5.0 specifically, we added gamer profile. There's now a centralized profile for all your gaming activity. Isn't that fantastic, right? Yeah, is that fantastic or not? Yeah, that's great. So you have a living game profile, and there you can store experience points, progresses in games, leaderboards, achievements, titles, and levels, all of that stuff. So that's good. We also added saved games. This allows you to persist game progress if you want to pause the game, for example. And you can also add an image to where the game was paused. And you can resume playing that game from that position on any other device that you have. So that's pretty great stuff as well. A big enhancement in Play Game Services for 5.0 is the introduction of events and quests. So what are these things? Let's start with events. Events are lightweight counters in your game. So it could be, for example, a player has opened a treasury chest in the magical room of floor 2 in the weird castle. Stuff like that. And this allows you to look at these events and how users are interacting with your game. So you can see which parts of your games are used frequently and which parts are not used so frequently. And that brings us over to quests. Because these events, you can then create quests based on those. So one example would be kill 5,000 zombies using a spoon before Sunday 8 p.m. Hey guys, we got to cancel that hiking trip. Yeah, it's the zombies again. No, it's with a spoon this time. Okay, great, right? So that's perfect. You can now have quests built right in there for you and available. And I think that that demonstrates that Google Play Services. Whoa! Bah. One more. Usually when I squeeze them in like that, they go really far. Ooh. There we go. That was a good shot. All right. There are I/O sessions, multiple I/O sessions on Play Game Services. You should definitely check them out. I don't think that mobile gaming will reduce, right? In terms, it will rather increase in terms of usage over the years. So there will be a lot of stuff that we can do in this. Activity recognition. This is one of my favorite areas because we're getting physical here. Previously, in activity recognition, you could detect the following different activities. If you were on a bike, if you were on a vehicle, if you were still or tilting or on foot. But we decided that that was not enough. So we added
walking and running.
That's right. We added walking and running to activities. And now we will have a live demonstration from Adam Metcalf, my colleague, who is working as a software engineer in the core Google Play Services team.
Oh,
or
hi.
core Google Play Services team, that's correct.
Hi, I'm Adam Metcalf. I'm a software engineer on the Google Play Services team. I thought I'd come up here and share a demo with you that I wrote that will be included in the samples section of the Google Play Services SDK. The demo is essentially activity recognition, including play games for a leaderboard and dumping some files onto Drive later so you can recap how it went. I will start it now.
Game started. Get ready.
This gives you enough time to put it in your pocket because we're going to do activity recognition.
Stop.
Oh, so stop, you mean be really still.
You're doing it.
Yay. This game is very much like red light, green
walking.
light. So it told me to start walking, so I'll start walking, and it takes about 10 seconds or so for the activity recognition to kick in because it wants to be very sure what it's actually, that you're not just shaking the phone. Walking on a stage is not the greatest place for this.
Keep it up.
Yay, there we go.
Stop.
Ooh.
Almost.
Oh, I was moving too much. I'm shaking up here.
Yes. All right.
Okay.
Start walking.
Okay, let's do this a little bit more.
You're doing it.
All right.
Yes.
All right.
All right. Start running.
Okay, let's see how this works on the
Almost.
stage.
Oh no.
Oh, no, come on.
Keep trying.
I can do it.
Keep trying.
Oh, no.
Stop.
Oh. All right, and that's going to conclude the game.
Keep it up. Game over. Your score was 775.
All right. So we can get that up on the screen when it comes up. So when the game concludes, it'll submit a score to the Google Play Games leaderboard. And because the Wi-Fi in this place is not the greatest, it'll do it offline and eventually send it up when I next get connected. You can see that it has a tracking of when I hit all the activity recognitions. And you can even open up a leaderboard and see how I'm doing. I did not beat my high scores, so I'll have to keep trying. All right. I think that's...
Round of applause for Adam. So that was an example of a game that used the location API, that used the leaderboards in Play Game Services, and that used the Drive API to store a file with the progress of the game. We had this slide as well. This shows you how these different clients within Google Play Services was connected to the Google API client, something you've probably seen. It's a new connectivity methodology in the core parts of Google Play Services. It makes these things, connecting different clients, really, really easy. So it's a very, very good feature. So now we have walking and running. That's exciting, right? We have a lot of stuff here now. It feels like you can build a lot of physical, interactive games if you combine all of these APIs. I'd like to see more of that coming out to Google Play. And I think this demonstrates that Google Play Services, that's right. Okay, there we go. All right, let's move over to Google Cast SDK. The Google Cast SDK was released in February 2014. This is amazing, right? Suddenly your mobile device, your Android device, becomes a remote control for any Chromecast-enabled TV screen. It's quite amazing, I think, what you can do with it from an application perspective. Together with that API, there is another API you can use, which is a Cast Companion library, which makes certain operations in the Google Cast SDK easier to do. So that's something to keep in mind. There's also an I/O session on Google Cast or a Chromecast, Casting to the Future, that you should pick up if you're interested in looking more into Chromecast. Now, Android, the Google Drive Android API was released in January 2014. This is a native API that allows you to interact with Drive content of any user that has given their consent, of course, for this. So this is a great way also to access the hard drives for different users. And this is a feature which is new in 5.0, which is great, I think. It's the App Indexing API. This API allows you, through Google Play services, to report things in your app, deep within your app, content deep within your app that gets picked up and becomes available to Google Search. And obviously, that can drive more user interaction with your app because you can actually now expose the stuff that you do deep within your app to the general internet. So it drives user engagement. Great feature as well. Google Fit. You should definitely go up to level 3 to check out the Google Fit station. This station will show you how to manage your fitness data. So that's a perfect place. And then dynamic security provider is an area that I'd like to touch upon as well. Dynamic security provider is a feature in Google Play services that will allow you to pick up a security provider. Now, if inner vulnerabilities is detected, for example, in SSL protocol or whatever, these vulnerabilities will be fixed as part of the push of Google Play services. That means that your apps that you're developing do not need to embed this kind of logic, and they don't need to be updated to cater for these different problems. All the security things are being dealt with the Google Play services push. All right, moving to the Google Maps Android API. The Google Maps Android API has been part of Google Play services for a long time now, since Android version 2.0. The version 2.0 has been part of Google Play services since December 2012. But just recently, we're happy to introduce, yes, this is a major feature, I think. It is the Street View capability of Google Maps. Let's introduce it with a round of applause, please. Get back to work, yeah. All right, this capability will allow your users to explore the world using panoramic 360 degrees views, right? And they can work with the Street View camera to zoom in and also control the camera location. And of course, all the movements that you do will be animated. These are now capabilities that you can get natively into your app. So it's a major extension. It's absolutely amazing. If you look at some of the things we just added to this, it's the Tubataha coral reef in Philippines. You can actually swim around in this reef and check it out using Street View. Another one that you may have seen before is that you can actually explore different base camps of Mount Everest. There's tremendous stuff in Street View that you can explore using this type of feature. And I thought, now when we have Street View, it's actually possible to create a dual time space, right? So given that we have location where I can register my current location, right? I could have Street View display my current location. So I could be walking down the street, right? I challenge for somebody to develop this app. I could be walking down the street, experiencing the real world with my body, but have the world that was recorded when the Street View camera passed by. I can get that experience at the same time. So kind of two time dimensions at the same time. And if somebody would come up to me and say, "You're crazy, what are you doing?"
Magnus is not here. He is traveling in time. Can I leave a message?
Then I could have that trigger. Absolutely amazing, right? We can build a time machine, a kind of a time machine, right? You're using these capabilities. And I think that this demonstrates that Google Play services. Whoa. Are you okay? Okay, that's good. That's great. There are also a couple of sessions on maps during this I.O., so go and check them out. There's also a Dev I.O. Byte available that you can check out on the internet. Great, so Google Play Services rocks, right? You can get the latest stuff we develop here at Google, latest and most shiny stuff that we develop in mobile technology. And that can be available to all of you mobile developers out there in the world to create great apps that are available on almost all of the Google Play devices out there. It's quite amazing. So we have social, we have activity, we have games, we have commerce, cast, location, drive, cloud, and maps. I'm happy I caught my breath between those. Otherwise, I wouldn't have been able to read that out in a single sentence. It is a fantastic framework for you to go out and create fantastic apps. In fact, it's your turn to go out there and create great apps. And don't forget to tell us all about it. Thank you so much for having us in this session. It was great talking to you. Adam, come up. So we have time for a couple of questions, I think. Yep. Go ahead.
Hi. So I was curious about, it's great that services are pulled out and you get the advantage of them being updated automatically without the user having to update your app. But in general, like with the Nokia X or the Amazon Fire, you can't get at some of these services without the Play Store. So are you guys thinking about offering an alternative, either like a library or some other way of getting at these services without the Play Store?
No, they're tightly integrated. The Google Play Store and Google Play Services, it forms the same concept. In fact, Google Play Services is an APK within the Play Store itself.
But certain things like GCM or ads or even analytics, I wouldn't say necessarily, like Wallet absolutely should be part of the Play services, but there's certain services that you can make a case that be beneficial to both Google and the developers that wouldn't be tightly integrated in Play services.
Okay. Well, right now, I think that the strategy is to have them together, bundled. Okay, next question. Over to the left.
Hi. I would like to know if the credit card scan feature is available without using Google Wallet. For example, with another payment method.
The what? Which feature?
The credit card scan.
As far as I know, that is an integral part of Google Wallet. So it works together with the Google Wallet account.
Okay,
Yeah.
thank you.
Thank you. Next question.
So it's awesome to see that Google Play Services is constantly evolving. But like some key APIs have been deprecated or removed, I think, recently, like Wallet Client and Plus Client. And it's not really always clear on the Google Play Services page, like what's deprecated and what's not, unless I go to individual pages.
Okay.
So what's the best way for me as a developer to plan ahead for these so I can make time to make these changes?
Question. You'll find out when you get to next SDK and get the warning messages in the compiler, I guess. Yeah. It's a good question. I don't have a good answer, but we have been looking at trying to get more information out preemptively about what has changed API-wise also, not only on the high level, new APIs that are being launched. So I'll take that as something to think about. Okay. Yep. Next question.
As Google Play Services continues to get larger and larger, are you thinking about breaking it up into modules optionally so developers don't have to include such a giant jar in their project files?
We've been looking into it. Nothing to confirm or deny yet.
Okay. Thanks.
All right. Next question.
I actually had the same question, although I've heard of a lot of developers running into this issue, especially with like actually running to the DEX limit with more recent versions of Play Services. So it's becoming like more and more of a pain point. Since you answered his question, I have another question, which is, what is tilting?
I think it's when there's been a significant motion, not significant motion, but it's like the user has picked up the device and there's been some amount of tilting to let you know that it was sitting down on a table or something and you picked it up.
So it's not like some weird phenomena that people are doing, no? Okay.
No, it's not like tilting.
All right, next question.
I'm working on an app that saves information as files in a file system. And I was thinking I would like to be able to synchronize that across several devices. So I was looking at the Dropbox API. It looks like the Google Drive might serve my purposes.
Yeah.
Would it serve my purposes? So would it be able to present the information as if it were a file system? And is there one of the problems with the Dropbox is, my problem is that it requires the inclusion of a lot of shared libraries. So I need to include a large shared library for every different processor.
Yeah.
And there's no shared libraries or anything. This is just a web service, the Google.
So the Drive API is a native API. It's statically compiled together with your binary. So there's not a web services API. And it allows you to do offline syncing with the device as well. And you can create offline folders and stuff. So it's a perfect API to access files such as in a hard drive with different users. It sounds like it's something you should check out.
Yeah, but it sounds like from the last two questions, I might have the same space problem because one of the problems I had with the Dropbox is required these two large shared libraries. It sounds like, but okay.
Okay,
Thanks.
thank you. 2 more questions, I think. Do we have time?
Go for it.
Are we okay with time? 1 minute, 1 question? 1 minute? 1 more question.
Okay,
You can do 2 more.
This one shouldn't count towards your limit. Will you shoot me with your T-shirt gun?
You don't want that.
You want me to shoot it?
Have you ever shot anybody with it?
No. Well, no, I haven't. But here, I'll shoot it one final time. Are you ready? Okay. Ooh, that's really far. It's way back there. That was a good final shot. Thank you so much for coming to this session. Ray Kurzweil is coming up. That's going to be exciting.
Hi, I'm Rick Viscomi, and I make YouTube fast. In this video, I'm going to share how we test web performance and a few tips for doing the same on your own website. The 2 test methodologies that we're going to look at are real user monitoring, or RUM, and synthetic testing. Real user monitoring, just as it sounds, gathers performance data from real users as they browse a site. For YouTube, this provides us with the ground truth about how users are experiencing the site. Synthetic testing, on the other hand, is more like a laboratory and is commonly used on demand to analyze a particular use case. Both methodologies collect performance data, but given these distinctions, RUM is especially useful for identifying how fast a page is, and synthetic for identifying how to make it faster. The simplest way to gather and analyze RUM data is with one of the existing analytics products. In fact, Google Analytics can do this for you. At Google, we use a custom solution called Client-Side Instrumentation, or CSI. RUM works on 3 basic levels. First, we instrument our client-side code to provide timing and page state data to the RUM JavaScript library. Then, the library packages up the data and sends it off to the analytics server for later use. And finally, the analytics server provides developers with a dashboard to view the results. Out of the box, most RUM tools measure the general page events published by the Navigation Timing API. But for us, one of the most important performance metrics is how quickly a video plays. The metrics you collect should be customized based on what your application does and what your users are actually waiting for. It's also important to include any contextual information that might have an effect on performance. For example, YouTube users may be exposed to experimental features, and we would need to know what effect that might have had on performance. By keeping track of these variables, we're better able to get insights into the performance of particular demographics. Also, note that the CSI beacon is sent unobtrusively after the critical path of video playback. This helps to ensure that testing does not interfere with the user experience. To analyze the performance data, we turn to the CSI dashboard. Here, we're able to look at the change in performance over time and compare experiments against controls. For example, in this chart, we're comparing the results of an experiment against the baseline control. The experiment times are lower or faster until the last point. We can use the CSI dashboard to slice data by various demographics to understand why this is happening. And when we break the data down by browser, it becomes clear that browser B is responsible for the regression. It's also worth mentioning that because we gather data from so many users, all of whom have different devices on different networks, we typically look at the 50th percentile, or the median value, to give us a representative view of performance data. Okay, that's it for RUM. Now let's compare it to synthetic testing. For that, we use Web Page Test, which is a free public tool. And instead of gathering data from real users, we configure synthetic tests to a particular demographic. The tests run in a laboratory-like environment to mitigate the effect of network anomalies, and this is achieved through repetition, so tests that are run many times are considered to be reliable. And finally, when the results are in, we're able to analyze our application-specific metrics along with the test network log. Web Page Test gives you full control over the type of use case for which you want to test. For example, we may be interested in the watch page performance in Chrome over a DSL connection. And being a free public tool, Web Page Tests are run on ordinary computers connected to the internet. To test YouTube, however, we need more privileged access to beta versions of the site. So for this reason, we run our own private instances of Web Page Test inside of Google. The results are shown on a waterfall diagram, which is a visualization of the network activity.
In this view, we're able to precisely see the activity on the critical path to video playback. And finally, Web Page Test also annotates the waterfall with our application-specific metrics. This gives us the necessary context to better understand what exactly is contributing to slow values. So that's it for our look at synthetic testing. Remember that RUM is only as useful as the metrics you provide. CSI is just one of many tools that does it, but your solution should be just as unobtrusive and lightweight. Synthetic tests should be configured to represent common use cases, like a particular browser, connection, or page demographic. Also, by locating synthetic test machines inside of your own network, you can validate performance on a staging server before launching. To learn more about the Navigation Timing API, check out the Mozilla Developer Network article at this URL. Or for more information on using Web Page Test, check out the link over here, and also look out for my book coming later this year. Thanks for watching.
Hi, I'm Alex Nixay, a senior engineer at Google. I lead the front-end team at YouTube. Over 6 billion hours of video are watched each month on YouTube. That's almost an hour for every person on Earth. At YouTube, we want to get that video to you as fast as possible. Since last year, we've reduced the time to start video playback by over a second. That's 40% faster. So where did we start in this optimization? We analyzed data from our real user monitoring, and we broke down the time it takes to start playback into critical stages. And we realized that one of those stages is the same for every playback, initializing the player. So we asked ourselves, what if we reuse the same player? The answer? It's faster. By maintaining a persistent player, we're doing less work on each navigation, and by doing less work, we're making each playback start sooner. So how did we do it? We built a new JavaScript framework for page navigation. Structured Page Fragments, or SPF for short, is a lightweight framework that handles navigations and updates to page sections. When someone first arrives at the site, the content is sent from the server and rendered normally. We call this static navigation. But when going to the next page, only document fragments are sent and page sections are updated accordingly. We call this dynamic navigation. So what does this give us? It gives us the fastest possible rendering time for that first page, leveraging all of our existing performance techniques. And it additionally allows us to maintain a persistent, responsive interface using the same rendering code as before. This all creates a better user experience. No one is staring at a blank white screen waiting for a page to load. But what about the developer experience? This framework allows us to maintain productivity by using the same code for both static and dynamic rendering. And it gives us the flexibility to use any server-side language and template system we want. It also supports sending data for use in client-side templating. So let's take a look at how it's implemented. We'll start with requesting content. Here's a link. Clicking it will trigger a static navigation request. Here's that same link using SPF. Clicking it will trigger a dynamic navigation request. As you can see, we use progressive enhancement and a simple syntax to enable SPF for supported browsers. Now let's look at sending that content back. Here's the HTML of a response for a static navigation. In this example, we use a common layout of upper masthead, middle content, and lower footer. Here's that same response using SPF. Only the fragment for the middle content is sent because the masthead and the footer don't need to change. JSON is used for transport during dynamic navigation. As you can see, the fragments for static navigation map directly to those for dynamic navigation, and this makes implementation very easy. Now, we won't cover them in depth, but SPF has several optional features that can help you improve your site. In some web apps, HTTP caching is inappropriate, but SPF allows you to cache responses in client memory according to your application-specific parameters. SPF can also prefetch responses automatically or manually to predictively boost performance. And SPF supports streaming multi-part responses in chunks to enable on-the-fly processing. This speeds up navigation by starting the rendering early. Now let's take a brief look at when YouTube launched these features and how they each impacted performance. Here's real data from YouTube's Real User Monitoring. I've graphed the median time to start playback for both HTML5, Flash, and the traffic-weighted composite of both. But for clarity, we're going to focus on the 5-day moving average of the composite. Now, when we first introduced dynamic navigation between consecutive video pages, we didn't have a persistent player yet, and we only saw a minor reduction in overall time to playback. Despite this, users reported that the site felt faster. This showed us that there are some very real user-perceived performance gains that dynamic navigation brings. Now, when we added that persistent player between consecutive video pages in Chrome, we reduced the overall time until playback by 8.5%. Expanding all supported browsers was another 9% improvement, and enabling on-the-fly processing over HTTP chunking yielded a 5% speedup. By defaulting supported browsers to our HTML5 player, we reduced our overall player initialization time and generated an 8% improvement. And then by dynamically navigating between all pages on the site, not just consecutive video pages, we were able to preemptively create a persistent player before it was even used, and this reduced our overall time until playback by 7.5%. When we expanded our default HTML5 player to both videos with and without ads, we yielded a 2% improvement, and finally, enabling on-the-fly processing over Speedy yielded a 4.5% speedup. And that's how we made it 40% faster to play a video on YouTube. So what's next? The great news is that we've open sourced the framework, so you can use SPF on your site. Check out our project page on GitHub to learn more. Thanks for watching.
Hi, I'm Mike from the YouTube desktop team, and I'm going to talk about how WebP helps to make YouTube faster. You may not realize it, but YouTube is one of the largest image hosting websites, serving tens of billions of video thumbnails every day. On many pages of YouTube, thumbnails can contribute up to 80% of total size. In fact, a typical page can easily contain more than a megabyte of image data. All those thumbnails add up. Client-side techniques like lazy image loading helps us to optimize rendering time, save bandwidth, and mitigate extensive backend load, but until recently we had no way to significantly optimize the images by themselves. Fortunately for us, it turned out that another team at Google has been working on the WebP image format that delivers a significant improvement in image size, up to 30%, while maintaining the same quality, so we decided to give it a try. By the time WebP wasn't a complete stranger to us, as we already used it for image sprites, but all the data we had was relevant only to lossless compression. So, earlier this year, we ran an experiment to encode a fraction of video thumbnails hosted at YouTube in lossy WebP. We aimed to measure the bandwidth savings and confirm that WebP helps to improve rendering time of web pages. Knowing about the benefits of WebP, we still had to consider that introducing a new image format is not free. At a minimum, it meant that we had to store multiple variants of the thumbnail, WebP version for clients like Chrome or Android, and JPEG for all others. In addition, we had to remember that on the client, WebP does cost a little bit more to decode. So we wanted to see if the benefits outweighed the cost. This experiment displayed an average savings of over 20% of transferred bytes and up to 10% improvement in page rendering time, which translates to a huge improvement in overall user experience. Not to mention that on the mobile clients, like our Android application, bandwidth savings were particularly helpful, as images are a significant contributor to data usage, even compared to video. So we've got a lot of great feedback from the users experiencing a smoother and faster UI. Based on these results, we decided to start encoding new thumbnails in WebP along with JPEG And as a result, WebP currently contributes to over 10% of all YouTube image traffic, saving terabytes of bandwidth every day, and we expect it to become as popular as JPEG in near future, especially as we enable it on our iOS client, TV and console clients, and allow third parties to use it too. We're very happy with WebP at YouTube, and I encourage you to consider it for your site as well. Check out the WebP homepage to learn about the format and on how to get started. Thank you.
Hello!
Hi!
Oh, hi! Today we are talking about YouTube and design. You know, YouTube's grown tremendously over the last 9 years and now has a global community of users, and that is a really interesting design problem.
I mean, if you're gonna have a problem, that's a good kind of problem to have, right?
Oh, yes, but it presents a challenge. And that challenge is, how do you design a product that looks and feels consistent when it means something different to everyone who uses it? You know, most brands have a pretty clear idea of how they want to be represented. But at YouTube, our challenge is that YouTube represents everything from delightful and silly content to serious and sensitive stuff.
That sounds like a pretty crazy challenge.
Exactly.
So why don't we share the story of how we took on that challenge and captured YouTube's brand?
Yes, sounds good to me. Everybody, this is Josh, and he's a product designer at YouTube.
Hi, and this is Michael. He's a marketing designer.
Yes. We work together on YouTube's user experience team. And Josh, let's tell these folks what they can expect in this video.
Sounds like a good plan. So in the next few minutes, we're going to cover a few things. The first is how a traditional style guide can actually be something much, much more than a style guide. The second is understanding your brand's identity through its community of users.
And then we can wrap up with some tips and tricks for how you can use this in your own work.
Cool. So we represent a collaboration between UX design and marketing, and we actually started building a traditional style guide, and then we kind of decided that we needed to do something different, and we ended up with something much, much more useful to our team. So here's just one page from what the style guide looks like.
Right. The guide we created lets teams at YouTube jam together on product design and content creation by speaking a common language. We can't go through the entire resource in this video, but we're going to share some of the content and process that went into turning YouTube Style Guide into a thought guide.
A thought guide? What's a thought guide?
Well, what do you think I'm thinking right now?
What are you thinking right now?
Yeah.
I think you're thinking that when YouTube first started, it was a video dating site. Am I right?
Yes, you are right, and that blows my mind every time. I love it. Good job.
Yeah, so since then, the site has evolved into an entire service, a huge service, and the video content on the service has grown up too.
YouTube is a platform for community movements like It Gets Better Project, memes like the Harlem Shake, and serious subjects like political uprisings captured on mobile phones.
And obviously YouTube gets all of its content from its users, so that means that our users are kind of designing our product with us. So why wouldn't our style guide actually reflect that?
Exactly what I was thinking. So we think it's way cooler to design with our community than for our community. I mean, not that we're not designing for our users, we are, but I mean, you know, like with them, like we feel like family, like the Brady Bunch.
Yeah, but that kind of presents a second question, doesn't it? Like, who makes up YouTube's community?
Well, you might think it's just people watching videos, but it's more complex than that.
So complex, actually, that we spent about a year doing research with users to learn how they interact with and relate to YouTube's brand.
Yes, here's some of that research. Here's a page from a diary study, and that looks like somebody using their tablet on the toilet. Is that accurate?
I'm afraid it is.
Well, that's fantastic, because we can use that. We like data. You know, sometimes research and analytics are used to solve a really specific problem, like how to improve task completion or click-through rates.
We were actually curious about larger communities and their needs on our platform, not just a specific persona and not just the people that are watching videos. So going back to that question, like, who really is everyone on YouTube?
Right. The YouTube community is really complex and diverse. There's a lot of people viewing videos, but that's not everyone. You know, there's also people making really interesting content, creating original videos, vlogs, shows, music, all of that stuff.
Yeah, and actually another thing that we found interesting is that advertisers were uploading amazing content and collaborating with our creators to make commercials and ads that people really loved to watch and actually wanted to share.
Right. So the research and digging into experiments, data, and YouTube's history revealed that there's real tribes of people collaborating on the platform. And that information is so much more interesting and valuable than it is for us to invent personas or to design for just one kind of user.
Yeah, so a style guide is usually there to document a brand in one direction. It's like a photo from one perspective. And we wanted something a little bit more dynamic, something that was more like a mirror that reflected principles back on the community.
Right, so if we had a mirror like that, we could use it to determine the success of our design solutions or campaign creative, the new metric being authenticity.
And it was that idea that started to turn our style guide into
All right, thank you. Hello, everyone. I'm RJ Michael. I'm Director of Games for Google. And it is my great pleasure to introduce you today one Ray Kurzweil. Ray Kurzweil is one of the world's leading inventors, thinkers, and futurists, with a 30-year track record of accurate predictions. He's called many things by a number of sources. He's called the restless genius by the Wall Street Journal, the ultimate thinking machine by Forbes magazine. PBS selected him as one of their 16 revolutionaries who made America. Kurzweil was selected as one of the top entrepreneurs by Inc. magazine, who described him as the rightful heir to Thomas Edison. Kurzweil was a principal inventor of the first CCD flatbed scanner, the first Omnifont optical character recognition system. He did the first Omnifont OCR. He did the first print-to-speech reading machine for the blind, the first text-to-speech synthesizer, the first music synthesizer capable of recreating the grand piano and other orchestral instruments, and the first commercially marketed large vocabulary speech recognition system. This is the stuff that the guy's done with his life, with his career so far. Among his many honors, he's the recipient of the National Medal of Technology. He was inducted into the National Inventors Hall of Fame. He holds 20 honorary doctorates, and he has received honors from 3 US presidents. Ray has written 5 national best-selling books, including the New York Times bestsellers, The Singularity is Near, in 2005, and more recently, How to Create a Mind in 2012. He is Director of Engineering at Google. He's now heading up a team developing machine intelligence and natural language understanding. He has also been a personal hero of mine since I was young. And he has this drive to make AI happen at Google. And I couldn't be more delighted to announce to you guys that as of today, I am now going to start exploring the entertainment and education space directly with Ray Kurzweil in his new organization. And who knows where this is going to go, but it's going to be awesome. Ladies and gentlemen, may I introduce Ray Kurzweil. Oh, God, it's just,
Thank you, and thanks, RJ. And now that you're going to be working with me, we have to work on your enthusiasm a little bit. And it's great to be at Google. It's actually my first job. I'll talk a little bit more about what I'm doing. But I'd like to share with you some ideas about thinking. I've been thinking about thinking for 50 years. First, I would like to say a few words about the law of accelerating returns. I won't say too much about it because many of you have heard me talk about it before, but the law of accelerating returns is alive and well. It's not just Moore's law. I keep hearing people saying, well, Moore's law is coming to an end, as if that were synonymous with the exponential growth of information technology. Moore's law was just one paradigm among many. When I first studied this in 1981, Moore's law had only been underway for a few years, which is shrinking components on an integrated circuit. In the 1950s, they were shrinking vacuum tubes to keep this exponential growth going. Gordon Moore originally said Moore's law would come to an end in 2002. Justin Ratner, the CTO of Intel, now says 2022. But he'll also show you in their labs the sixth paradigm, three-dimensional self-organizing molecular circuits working, which will keep the law of accelerating returns going well into late of this century. So what is the law of accelerating returns? It's not that everything grows exponentially or even every aspect of information technology. We were speeding up transistors, making them smaller so the electrons had less distance to travel, so transistors were faster. That was a sub-paradigm. I always felt we were going too fast. The human brain is actually very slow, computes about 100 calculations per second in the interneuronal connections, but it's massively parallel. It actually has 100 trillion-fold parallelism. There's 100 billion neurons with about 1,000 to 10,000 connections each, and that's where the computations take place. So it's very massively parallel, but slow, so it uses very little energy, and we needed to move more in that direction towards more parallelism and less speed. So speeding up transistors was just one sub-paradigm. And we already have taken steps in the third dimension. Many memory circuits are already three-dimensional. The law of accelerating returns is not limited at all to Moore's law. Moore's law is one paradigm among many in computation. Computation is one example of many of the law of accelerating returns. So what exactly does it pertain to? It pertains to the price, performance, and capacity of information technology, and every form of information technology. So in computation, calculations per second per constant dollar has been speeding up at an exponential pace since the 1890 census. But it's also true of communications, biological technologies, brain scanning, modeling the brain, being able to reprogram biological data, printing, the spatial resolution of three-dimensional printing, which is turning information into physical products. These are all examples of either price, performance, or capacity of information technology. And I'll show you this first example. I mean, this is the graph I had in 1981 of computation. It's a logarithmic scale. Every label level is 100,000 times greater than the level below it. And so this represents trillions-fold increase in calculations per second per constant dollar. Moore's law is the fifth paradigm. But notice how smooth a trajectory that is. It really has a mind of its own. It goes through thick and thin, through War and Peace. And exponential growth, the second point I want to make, is not intuitive. If you ever wonder, gee, why do I have a brain? It's really to make predictions about the future so we can anticipate the consequences of our action and the consequences of inaction. But those built-in predictors are linear. When we were walking through the fields 1,000 years ago, we would make a prediction. Okay, that animal's going that way. I don't want to meet him. I'm going to go a different route. That was good for survival. That became hardwired in our brains. But those predictors are linear. And people still use their linear intuition about the future. That's the principal difference between myself and my critics. We're both looking at the same reality. We have similar judgments about it. And if I thought progress was linear, I'd be pessimistic also. And many things are linear. Biology, health and medicine was linear. That was still useful. The life expectancy was 19 1,000 years ago. We've quadrupled it. I talked recently to some junior high school students and pointed out they would all be senior citizens if it hadn't been for that progress. Life expectancy was 37 200 years ago. Schubert and Mozart died in their 30s of bacterial infections, and that was typical. That's all been from linear progress. Exponential progress is quite different. A linear progression, that's our intuition about the future, goes 1, 2, 3. An exponential progression, that's a reality, not of everything, but of price, performance, and capacity of information technology goes 1, 2, 4. Okay, it doesn't sound that different, except by the time you get to step 30, the linear progression, our intuition's at 30, the exponential progression is at 1 billion. And that's not an idle speculation. I mean, this is several billion times more powerful per dollar than the computer I used when I was an undergraduate at MIT. It's several trillion-fold since we started with the 1890 American census. But again, look at how smooth the progression that is. Nothing has any impact on it. The third point I want to make is that it's not just computation. It really affects every form of information technology, and information technology is ultimately going to transform everything we care about as a result of application developers like yourself. I mean, that's what drives it forward, and I'll say more about that. We could buy 1 transistor for $1 in 1968. I was pretty excited about that because I was used to spending $50 for a telephone relay that could do that. We can now buy 10 billion. Cost of a transistor cycle has come down by half every year. That's a 50% deflation rate. So I can get the same computation or communication or biological technologies as I could a year ago for half the price. Economists actually worry about that because we had massive deflation during the Great Depression. A different reason, that was a collapse of consumer confidence. But the concern is if I can get the same stuff, and I'll talk about three-dimensional printing in a moment, so I do include physical stuff, for half the price, I'll buy more. I mean, that's economics 101, but I'm actually going to double my consumption. And if I don't, let's say I increase my consumption in terms of bits and bytes 50%, which is a lot, the size of the economy, not as measured in bits, bytes, and base pairs, but as measured in currency, will shrink. For a variety of good reasons, that would be a bad thing, but that's not what happens. I've got 50 different consumption charts like this. This is bits of memory consumed. We actually more than double it every year. There's been 18% growth in constant currency each year for the last 50 years in every form of information technology, despite the fact that you can get twice as much of it each year for the same price. And the reason for that is application developers like all of you. I mean, why weren't there social networks 8 years ago? Was it because Mark Zuckerberg was still in junior high school? No, there were attempts to do it, and there are arguments. You know, can we afford to allow our users to download a picture? The price performance wasn't there. Why weren't there search engines, more than 15 years ago? I wrote in the early 80s, when the ARPANET connected a few thousand scientists, that this was growing exponentially, would necessarily do that. This would therefore be a World Wide Web, I didn't use that term, connecting hundreds of millions of people to each other and to vast knowledge resources by the late 90s. People thought that was nuts when the entire American defense budget could tie together a few thousand scientists, but that's the power of exponential growth. That's what happened. And I wrote that there'd be so much information, you couldn't find anything without search engines, and the computational and communication resources needed for a search engine would come into place. What you could not predict is that it would be these couple of kids in a Stanford dorm near here who would take over the world of search among the 50 projects that were seeking to do that. I'm not saying everything is predictable, but you could predict that search engines would be needed and feasible in the late 90s, and Google was founded in 98. So Time Magazine wanted a particular computer they had covered as the last point on this cover story about the law of accelerating returns. It's right there, and this was a curve I had laid out 30 years earlier. So this is, in fact, very predictable. And in terms of all my predictions, when they're like this, in terms of actual numbers of price performance or capacity of different information technologies, they're really right on the money. If you Google how my predictions are faring, you'll get a 150-page essay looking at all the predictions I've made as of that time, which was a couple of years ago, including 147 that I made in The Age of Spiritual Machines, which I wrote in the late 90s, came out in 99, about 2009. 78% were exactly correct to the year, and these were predictions that were by decade. Another 8% were off 1 year, so I called them essentially correct. So 86% were correct or essentially correct. The ones that were wrong, included things like regulatory and cultural issues. Like, for example, one that was wrong is that we'd have self-driving cars, which in fact began a glimmer of working in 2009. If I had said 2014, it would have been correct because The Google self-driving car has already gone 800,000 miles, and Google's going to launch a fleet of experimental vehicles in Mountain View this year, but it wasn't correct for 2009. The number of bits we move around wirelessly in the world, there was Morse over the last century. There was Morse code over AM radio a century ago. Today's 4G networks, trillions-fold increase. But again, look at how smooth a trajectory that is. Internet data traffic doubling every year. Here's that graph I had of the ARPANET in the early 80s and projected that out. The graph on the right is the same data, but on a linear scale, and that's how we experience it. We don't experience it in the logarithmic domain. So to the casual observer, it looked like, whoa, World Wide Web, new thing, came out of nowhere, but you could see it coming. And biology, this has been a perfect exponential. The Genome Project was announced in 1990. It was not a mainstream project. Halfway through the project, critics blasted it, saying, look, you're halfway through this 15-year project. You've only collected 1% of the genome. So 7 years, 1%, is going to take 700 years, just like we said. My reaction is we're at 1%. We're almost done, because it's an exponential progression. And indeed, it was done 7 years later, because 1% is 7 doublings from 100%. That's continued since the end of the Genome Project. That first genome cost $1 billion. We're now down to a few $1,000s. But it's not just sequencing. We can now reprogram this outdated data. And there are many examples of that. At the Joslin Diabetes Center, they turned off the fat insulin receptor gene. We have technologies like RNA interference that can turn genes off. These animals ate ravenously and remained slim and lived 20% longer. I've worked with a company that adds a gene to patients with a terminal disease called pulmonary hypertension caused by one missing gene. They scrape out these cells non-invasively from the throat, add the gene in vitro, inspect it got done correctly, replicated several million-fold, another new technology. So they now have millions of cells with that patient's DNA, but with the gene they're missing, inject it back in the body recognizes them as lung cells, and this has cured this terminal disease in human patients. There's an interesting case combining a number of different exponentially growing information technologies with this young girl who had a damaged windpipe. She was not going to be able to survive with it. So they scanned her throat with non-invasive imaging. Spatial resolution of non-invasive imaging is doubling every year. That's an important technology for reverse engineering the brain. Designed her a new windpipe in the computer using computer-assisted design. Printed it out with a 3D printer using biodegradable materials. Then populated this scaffolding with her stem cells using the same 3D printer. Grew out a new windpipe for her, installed it surgically, and it worked fine. You can now fix a broken heart. Not yet from romance. That'll take us a few more decades. But half of all heart attack survivors have a damaged heart. It's called low ejection fraction. My father had that in the 60s and could hardly walk. Now you can fix that by reprogramming adult stem cells and rejuvenating the heart. You have to be a medical tourist because it's not yet approved here, although it will be soon. There are many other examples. We could talk all day about this, but our ability to reprogram this outdated software is growing exponentially. These technologies are now 1,000 times more powerful than they were a decade ago when the Genome Project was completed. They'll be another 1,000 times more powerful in a decade, 1,000,000 times more powerful in 20 years. That's the implication of a doubling in power every year. Somewhere between that 10 and 20-year mark, we'll see significant differences in life expectancy, not just infant life expectancy, but your remaining life expectancy. The models that are used by life insurance companies sort of continue the linear progress we've made before health and medicine was in information technology, which was based on basically accidental findings. This is going to go into high gear. Life expectancy is a statistical phenomena. You could still be hit by the proverbial bus tomorrow, because we're working on that here at Google also with self-driving cars. And three-dimensional printing, I think we're in the hype phase of this. I've written about the life cycle of technologies. They're usually early enthusiasts who see the vision, but haven't really calculated the timing correctly. And exponential growth ultimately becomes transformative, but it actually starts out very slowly. You're doubling tiny little numbers, like 1/10,000th of the genome in 1990, 2/10,000ths in 91. So the progress doesn't come unscheduled, disillusionment lets in, and then you have basically a bust, and then it comes back as we really truly understand the true markers of what it will take to be successful. This looks like a young audience, but you may remember the internet boom in the 1990s. You know, if you had the URL dog.com, you were a billionaire. Then around the year 2000, people realized you can't really make money with these internet companies, and there was the internet bust, which almost took down the economy. But then it came back, and today you have internet companies like Google and Apple and Facebook that are worth, hundreds of billions of dollars. And we're kind of in that hype phase now. I think we're still 5 or 6 years away from the parameters we need to make this successful. We need submicron resolutions. The resolution accuracy is improving at a rate of about 100 in 3D volume per decade, so it's exponential progress. But right now it's multi-micron. We can do interesting things. We had an opening a year ago at Singularity University where the band, all the instruments that the band was playing were printed out on a three-dimensional printer. So they're interesting niche applications. But by 2020, we'll be able to print out clothing, for example. So people go, great, there goes the fashion industry. But not so fast. I mean, look at other industries that have already undergone the transformation from physical products to digital products. A few years ago, if I wanted to send you a book or a movie or a music album, I'd send you a FedEx package. Today, I can send you an email attachment. And there's indeed an open source market with millions of free songs, videos, movies, books, documents that you can download legally for free, and you can have a very good time with these free media products. But people still spend money to read Harry Potter or go to the latest Blockbuster or get music from their favorite artists. And you have the coexistence of the open source market, which is a great leveler, bringing high-quality products to everyone at almost no cost or no cost, and a proprietary market. That'll be the nature of the economy going forward. So in the 2020s, you'll be able to download cool fashion designs, print them out at pennies per pound, which is what it costs for three-dimensional printing. But people will still spend money for the latest hot designs from their favorite designer. And I mentioned I've been thinking about thinking for a long time. 50 years ago, I wrote a paper when I was 14, how I thought the brain worked. There was actually very little to go on, but I described it as a series of modules, and each module could recognize a pattern, and that the essence of the human brain was pattern recognition. We actually weren't very good at logical thinking. Even then, I could see that chess computers were based on logic and being able to look ahead and calculate all the move, counter-move sequences. The human brain did it by deep forms of pattern recognition. In '97, Kasparov was asked, Deep Blue analyzes 200,000 board positions a second. How many do you analyze? And he said maybe less than one. So how is it that he was able to hold up at all? It's his deep powers of pattern recognition. And I described it as a series of modules, each of which could learn a pattern, remember a pattern, implement a pattern, discover a pattern, and that these were organized in hierarchies, and we created that hierarchy with our own thinking. And that the whole neocortex worked the same way. And that was actually contrary to the common wisdom at the time, because it was noticed that these different regions, and they do very different things, so it was thought they must be organized very differently. V1 in the back of the head recognizes visual images, because that's where the optic nerve spills into, and it can recognize the fact that the edge of this table is flat, that there's a horizontal crossbar, and that capital A, and so on. The fusiform gyrus up here recognizes faces. We know that because if you conk somebody over the head in that region and knock it out, people can't recognize faces. The frontal cortex is famous for language and art and science. They do very different things. They must be using different algorithms. There was one neuroscientist who actually did autopsies of the neocortex in all of these different regions and found they looked exactly the same neurons, the same interconnection patterns. He said neocortex is neocortex, Vernon Mountcastle. And so I used that, and I also used observations of human brains in action, which is still our best laboratory, and described this basic method. This actually describes the same algorithm, and actually describe how each of these modules, which I count now at 300 million, can recognize a pattern and learn a pattern. It's basically functionally similar to a hierarchical hidden Markov model, which is a technology I worked on in the 1990s in speech recognition and early forms of natural language understanding. And it's a little bit different than neural nets because neural nets, the basic element is a neuron which can kind of learn one state, not really a whole pattern. And in my view, the basic module is a pattern recognition module that can learn a more complex pattern. And a hierarchical hidden Markov model is a hierarchy of Markov models, each of which can learn a fairly complicated pattern. And I believe that is how the human brain works. And that's what I'm doing here at Google. I'd given an early version of this book to Larry Page a couple of years ago. He liked it. I met with him to ask him for an investment in the company I was going to start to develop these ideas. And he said, have you thought of doing this here at Google? We have these terrific resources in terms of data and computation and talent. He actually said it in a very low-key way, but that was his message. So I met with him, Alan Eustace, who's here in the audience, and they said I'd have kind of independence I'd have with my own company, but these Google resources, and so I've been doing that now for a year and a half, and it's been terrific. It's really the only place I could do this project, which has been a 50-year endeavor. And the spatial resolution of brain scanning, as I mentioned, is doubling every year. We can now see inside a living brain, see it create your thoughts, see your thoughts create your brain. And there's a few significant milestones in the history of the biological version of this thinking. You can see it up there, the neocortex. The neocortex emerged 200 million years ago with mammals. It was capable of a different type of thinking, basically hierarchical thinking. Other animals could learn things, but not with elaborate hierarchies. They could have a behavior that might have a hierarchical aspect to it, but it was fixed. They couldn't learn a new hierarchy, at least not in one lifetime. Maybe over 10,000 lifetimes they could evolve a new behavior. Next significant thing that happened 65 million years ago, there was a violent change in the environment. We call it the Cretaceous extinction event. That's when the dinosaurs went extinct. That's when 75% of all the animal and plant species went extinct. And that's when mammals overtook their ecological niche, because they could adapt their behavior quickly enough to cope with it. Next significant milestone was 2 million years ago. We developed these large foreheads, so we now had more neocortex. That neocortex has all these folds and convolutions basically to increase its surface area. It's a flat structure. It's about the size of a table napkin and just as thin. It's one module thick, but it has so many convolutions and ridges, it's 80% of your brain. And the frontal cortex, it's often been thought it must be qualitatively different because it does these amazing things like art and poetry. But recent research projects discovered or examined the issue, what happens to V1, which I mentioned is in the back of the head, and does these very simple things like the fact that that's a straight line. What happens to it in a congenitally blind person? They're not getting any visual images. The frontal cortex notices, hey, V1 isn't doing anything, and it actually harnesses it to help it with language and art and science. At the opposite extreme end of the continuum of complexity of features, showing they're both basically using the same algorithm. And so we were already doing a very good job as primates without the frontal cortex. Now we had this additional quantity, and so we could think higher thoughts, because the neocortex is built on conceptual levels. Each level is more abstract than the one below it. So the first thing we invented was language, and that was about a couple 100,000 years ago. So I have an idea in my head. It's a hierarchy of other ideas and symbols and other structures, and I want to actually communicate that and basically transmit that hierarchical structure to your neocortex. So we invented language in order to do that. And it's a communication medium that is hierarchical, so it could reflect the hierarchical structures in the neocortex. And neocortex was successful because the world is hierarchical, and it's the best way to understand it. Trees have limbs, limbs have branches, branches have other branches, some branches have leaves. The world is organized in a hierarchical fashion, and we could now represent this in language. And if you ever want to see some entertaining examples of the hierarchy in language, read Gabriel Garcia Marquez novel. He has one sentence that's 6 pages long, and it's grammatically correct, and it has a fantastic array of hierarchical structures showing the indefinite hierarchy we can create with language, reflecting the indefinite hierarchy we can have in our ideas. And there's then been a continual acceleration of technology. Written language only took a few thousand years. The first examples were thousands of years ago. The printing press took 400 years to reach a mass audience. The telephone reached a quarter of the American and European population in 50 years. The cell phone took 7 years. Social networks, wikis, and blogs took 3 years. We continually are accelerating basically these information technologies because of the law of accelerating returns. And we can now simulate aspects of the neocortex. And fundamentally, what my team, and we're not the only team doing this, is trying to create a functional simulation of the neocortex. And I'll tell you the key problem is we can create hierarchies. So even in the 1990s, we had a hierarchy of acoustic states, and then phonemes, and then word models for speech recognition, and then simple grammatical models so that we could have a sentence like move this paragraph after the third paragraph in the next page, and it would carry out that simple command. But we couldn't actually add a new layer ourselves. That's actually, if you want to speak technically, the key technical challenge in trying to create more flexible AI is how do we create the next conceptual level that's more abstract than the ones we have automatically from the data, rather than reprogramming it ourselves using our human intelligence. So I'll skip some of this to... at the very high level, you have very abstract ideas, like that's funny, that's ironic, she's pretty. This 16-year-old girl was having brain surgery, and whenever they stimulated these points showed in red, she would laugh. They wanted to be able to talk to her. There's no pain receptors in the brain, so you can do that during brain surgery. And they thought they were stimulating some kind of laugh reflex, but they quickly realized that no, they were triggering the genuine perception of humor. She just found everything hilarious whenever they stimulated these points. You guys are so funny just standing around was a typical comment. And they weren't funny. So an example from another company that shows our beginning ability to actually understand human language is Watson. As you can see, Watson got a higher score than the best 2 human players at Jeopardy combined. It got this query correct in the rhyme category, a long, tiresome speech delivered by a frothy pie topping. And Watson quickly said, "What is a meringue harangue?" And Watson got its knowledge by reading 200 million documents of natural language, including all of Wikipedia and other encyclopedias. Doesn't understand each page as well as you or I, but it makes up for that by reading a lot of pages. And that's the kind of thing we're trying to do here. We have a model that I believe actually will solve this key problem of being able to add to the hierarchy automatically so that we can handle ultimately complex documents. So one application, for example, would be in language translation. Right now it does a very good job through the power of data and these Rosetta Stone databases of translated text by matching word sequences. We're improving the way that we match them. But we really would like to do it the way a human does it, which is to understand it. What does it mean to understand? It means to take the language and actually create this hierarchical structure of the ideas in my head and then re-synthesize it, re-articulate it in the new language. That's the kind of thing we hope to do. We'd like the search engine to read for meaning. So if you put out a tweet, everything Ray Kurzweil is saying at I.O. is nonsense, there's actually, in that simple text, a hierarchy which you need to understand to really understand what that's trying to say. If you write a blog post, you have something to say. Now, search already goes substantially beyond the base forms. It'll understand the syntactic structure. If you use the word he, it'll do that co-reference resolution. It'll understand synonyms. But it's not fully modeling the ideas that you have to say when you write an article or a blog post. And that's what we would like to actually understand. And then you would be able to dialogue with your search engine to give it complex tasks and interact with it the way you would with a human assistant. And it would then go out, and maybe it wouldn't even find the information that day, but a week later it would pop up and say, oh, you know, you asked me this question a week ago, and new research just came out that answers that question, and so on. So let's stop here, and I notice our time clock isn't working, so I have no idea where we are, but RJ, maybe you've got some questions.
Yes, indeed. So I've gathered up some questions from people, fellow Googlers, from some of our friends throughout the community. And we're going to take this opportunity to ask some of these questions. Starting with a quote from William Gibson, the famed author, who said that the future is here, it's just unevenly distributed. Where do you think things are running fast, and where are they lagging further behind than what you would have expected?
Well, I think it's actually very widely distributed. Companies like Google, and not just Google, I mean, Apple, Microsoft, Facebook, are not just using these technologies with a few corporations and government agencies. It's in billions of hands. Google Search is used between 1 and 2 billion people, and and we hope to expand that to the next couple billion users and a couple billion after that. That's the business model, and I believe that is actually how we will use these technologies. They'll be very widely distributed, and they're very democratizing. The technologies that move very smoothly are the sort of pure application of the law of accelerating returns. When you get into regulatory issues like we have with the self-driving cars, and it's maybe a little less predictable. There's a lot of regulation in medicine. But I believe these technologies ultimately will be so profoundly superior that they will actually accelerate these regulatory processes as well.
So you outline in your book, How to Create a Mind, the idea of what it's going to take to actually create a mind. And you've chosen to pursue these ideas here at Google. Why Google?
Well, it's actually the first time I've done that, but I've realized that you need unique resources to do this. It's a very difficult problem. So for one thing, you need a tremendous amount of talent. That's, I think, the primary resource. It's unique. Maybe not completely unique, but it's certainly evident at Google. And then, you want to run something on 1 million computers, and you want tremendous data that reflects language. I mean, we have, tens of billions of pages, virtually all books and web pages. And so this is not a project I could do with my own company, even if I raised all the money that I could hope for. And it's a bold company that takes on major challenges and tries to improve the world with these applications and make them widely available. So I like the philosophy of the leadership.
Me too. It's true. So, but I'm an engineer at heart, and the engineer in me wants to know how you intend to build this thing. Could you describe to us what the engineered mind is like? What tech must we implement versus what behavior do we expect to emerge? What must be done in software? What must be done in hardware?
Well, on the hardware requirements, I mean, to functionally emulate a human brain, I've analyzed that. I estimated at about 10 to the 14th calculations per second in singularities near. So I hedged that a bit and said 10 to the 14th to 10 to the 16th. I've reanalyzed it using different methods in How to Create a Mind that come up again with 10 to the 14th. There have been a number of independent analyses of that come with the same figure. We've already surpassed that, like 3 orders of magnitude in supercomputers. It'd be hard to provide 10 to the 14th calculations per second to all of a billion users, kind of using it, more or less at the same time. I've discussed this with Larry Page, and he thinks, no, actually, that could be possible. But the law of accelerating returns will make that easy, by the early 2020s. So it really comes down to a software problem. I described, I think, the key software problem. We can already create these hierarchies. In Google and in other companies, there's debate between several different learning methods, and they have pros and cons. We need one that can actually represent hierarchies of complicated patterns, where each pattern has its position in a complicated hierarchy of patterns. And the key unsolved problem is how do we then add a conceptually more abstract level to that? And I think we can use machine learning to find the patterns, at that high level, but you need to be able to model them correctly. And so that's what we're exploring, and then applying it to language. And ultimately, Google will apply it to other types of input, like videos and pictures. And we're already making a lot of progress. The machine learning at Google is already very powerful. Once we have a system that's working, there will be little loops that are very tight that are taking up the bulk of the computation that we could put in an ASIC in a dedicated circuit, because you can get a 1,000-fold increase in price performance by hardwiring repetitive algorithms in hardware. And there are attempts, of course, to do that. I think it's premature now because we haven't really settled on the right type of machine learning, so we don't really know what algorithm to speed up. But that'll be a straightforward engineering trade-off once we can actually master the software. So it's fundamentally a software problem.
So most of the people in this room are engineers or heavily involved in app development as well. And everything that you're talking about here, these are exciting visions to a lot of the people here and myself as well. But what can the developers in this room do to turn these ideas of yours into actual working products and systems? What role do these developers play in pushing all of this forward for us?
Well, it's application developers that drive it forward. And I mean, there's a debate in the AI field between traditional artificial intelligence and something called AGI, artificial general intelligence, which is implicitly a criticism that AI has not pursued general intelligence and has gone off into narrow things like OCR, or speech recognition, or robotics. But I actually think we get from here to there being future AI, strong AI, one step at a time, and the steps are applications, and we need to actually optimize the technology for the applications. It's very hard to develop a technology if you don't have something to optimize it for. And so I like the idea of crossing the river kind of from one stone to the next. People say, well, what about that part of the river where it's too deep and there are no stones? So, well, I'm not sure of the answer to that. But we do get from here to there through one step at a time. And each step is sort of benign. It's exciting in the application world, but it's not, the grand step to AI. But that's how we're going to get there. And the application developers push it forward and make it practical and provide an economic business model for it.
So this law of accelerating return that you talk about, you've made it clear in natural space that it exists like this, and in the technology space, it's definitely true. It all starts to feel just like natural law, like natural progression. Why do we have to work toward it? Why don't we just sit back and let it happen for us?
Yeah, that question comes up a lot. Why don't we just sit back, let it happen? Why are we working so hard? And if we did that, it wouldn't happen. So what is actually predictable is the human passion to make improvement, to use the computers of 2014 to create the computers of 2015. We couldn't do that a decade ago. We're able to improve things in an exponential manner. If things are 1x, we try to make it 2x. If they're 1,000x, we don't seek to make it 1,001x. We try to make it 2,000. And we have the tools to do that. Having a mathematical treatment in singularity is near. The empirical data is the strongest evidence for the law of accelerating returns, but it is driven by application developers and technology developers taking each step with the current state of the art.
Now, speaking of the curves and the rising curves, sorry, I lost my place on my page here. Well, so let's talk about specialized smarts then. There's a role for specialized smarts, and the neocortex seems to have a very general architecture, repeated architecture as you were mentioning. But there also seems to be specific modules that have evolved. Do you think there are specific functions that we're going to need to build for our learning machines? And how do you know when to go really specific and focus on one particular thing versus just allowing it to be handled by the general architecture?
Well, we still have the old brain, like the amygdala puts out an ancient cascade of hormones to prepare us for fight or flight. It's no longer able to decide what to be afraid of. So your boss walks in the room, and whether that causes laughter or fear is really up to the neocortex. And the neocortex is a general architecture. There are no specialized regions. There's no music region. But the patterns in music, or even particular types of music, whether it's Chopin waltzes or hip-hop, are specialized types of knowledge. And we have a limited capacity in neocortex. So you can really be a world-class master of one thing. Einstein played the violin, but he was no Jascha Heifetz. Heifetz was interested in physics, but he was no Einstein. We really need to devote the bulk of our neocortex, it's not devoted to everyday concerns, to one type of knowledge, which has its own type of patterns, and learn the patterns that others have created and then push it forward. But really, the architecture is pretty much the same.
I find that fascinating. It's the same algorithm repeated. So while it's great for all of us that personal technology has been freeing us up and empowering us all, giving us a lot more free time and giving us more capabilities under our fingertips, do you think that we are actually going to make good use of it? The thing that I keep wondering about is, are we going to essentially use this free time and all these extra capabilities that computers give to us to allow us to watch more television and consume more sugary snacks, which is what I'm afraid of. So how are we going to use this technology that you're developing to ensure that we actually will live better?
Well, there's always pros and cons. We just happen to be on the right slide here, and this is just one perspective. People quickly lose perspective. We forget what things were like, 8 years ago before there were social networks, 15 years ago before there were search engines. Once these things happen, we assume they've always been around. People certainly forget what things were like 200 years ago when Thomas Hobbes described life as short, brutish, disaster-prone, poverty-filled, disease-filled. We'll take a quick 1-minute trip through the last 2 centuries. These are countries. The big red circle is China. It does some interesting things. Keep an eye on that. The x-axis is income per person in today's dollars, so you can understand it. So there were wealthy countries and poor countries, but nobody was very wealthy. Income per person was hundreds of dollars in today's dollars. On the y-axis is life expectancy in the 20s and 30s, worldwide average 37. So this was the beginning of the Industrial Revolution, started in the textile industry in England in 1800. A few countries were making progress. But as you get to the 20th century, the 1900s, you'll see a wind that carries all of these countries towards the upper right-hand corner of the graph. The have-not divide does not go away. There's still rich countries and poor countries, but the countries that are worst off at the end of the process are far better off than the countries that were best off at the beginning of the process. And I shouldn't say end of the process, because the process isn't ending. It's going to go into high gear as we get to the more mature phases of the biotechnology and three-dimensional printing revolutions, AI, and so on.
That's just awesome, man.
So to be continued.
So, and I think we might have a few minutes left to take some questions from the audience at this point. Is it a...
Well,
there's 2 more left to ask, but I'm saving those babies for the end, unless you have something you wanted to address.
Well, I don't know how much time we have, because the countdown clock isn't working.
Yeah, the countdown clock's up. We have 2 minutes left? Oh, 2 minutes.
Okay.
Oh, all right. Well, then I'm going to stick to my questions then. Sorry, you guys. Because I've got one that is just one of my favorite interview questions. And I've been dying my whole life to ask Ray this question. So, if you would tell us, please, what are some of the more humbling experiences you've had researching and developing your concepts over the years?
Well, I think it's this one unsolved research question that the human brain is able to do, and I think it's the key to making further advances in artificial intelligence. The neocortex is organized in these layers, and each layer is more abstract than the one below it. And we're able to actually, if we understand something, like we understood speech recognition, we can actually identify, okay, phonemes should be here, words should be here, and we can create that hierarchy and then use machine learning to learn each level. But how do we then create a more abstract level on its own? Because the neocortex does that. I've been watching my grandson go through level after level. Now he's almost 3, and he's got quite a few levels under his belt. And that's done with the neocortex without really any external input other than his parents, saying, that was good, Ethan, or Leo. So how do we do that? That's what we hope to solve. I think we can find, have a stable set of hierarchies and then find patterns at that level using machine learning and then automatically add a new level. But that has never been demonstrated, and if we could do that, I think we'll make great strides in artificial intelligence. But so far, that has eluded the AI field.
So then I'll end with this. You mentioned your grandchild, 3-year-old. There's certain definitions of the word consciousness that would suggest that a 3-year-old has not yet achieved consciousness, awareness of self, awareness of what's in the mirror, and things like that.
Well, he would disagree with that. But.
Yeah. So I would like to end then with 3 simple questions that I would ask you to take all together for us. What is consciousness? What is free will? And what is soul?
Well, I always thought you had a good sense of humor. So, 1 minute should be plenty for that. We've debated that for thousands of years, going back to the Platonic dialogues. But to summarize, consciousness, whether or not an entity, has consciousness is not a scientific question, because there's no experiment you could run that would really definitively, a falsifiable experiment that you could run whether or not an entity is conscious or not. We assume that each other is conscious, that human agreement falls apart when we go outside of human experience. People disagree about animals. They will disagree about future AIs. An AI could claim it's conscious. Eugene Gustman claimed that he was conscious, but it wasn't very convincing. And so so some scientists say, well, it's not a scientific question, it's not important, we should dismiss it, it's just an illusion. I think that's a mistake, because our whole moral system is based on consciousness. So you need a leap of faith. My leap of faith is that if an entity seems conscious and seems to be having the subjective experiences it claims to be having, I'll believe it's conscious. I would also make an objective prediction that most people will accept the consciousness of these entities. And so a valid Turing test, I have a long now Turing test bet with Mitch Kapor that by 2029 a computer will pass the Turing test. And we actually set a very difficult set of rules. I think if an AI passes that, people will really be convinced that it's really conscious, and we will accept it as having those subjective experiences. Identity is really continuation of a pattern. People say, well, what are you talking about? Your identity is this, your physical stuff. It's this flesh and blood. But actually, this is very different than it was 6 months ago. All of our cells turn over, some in hours, some in days, some in weeks. The different components of the neurons, the tubules, the ion channels, the filaments change over in either hours or days or weeks. I'm completely different stuff than I was 6 months ago. So I make a comparison to water in a stream. It may make a certain pattern of as it goes around a rock. That pattern can stay the same for days, weeks, years, but the water actually changes in milliseconds. So is that the same river? And there's a Chinese proverb, you can't walk in the same river twice. But it's actually a continuation of a pattern, and that's what we are. The pattern changes slowly, but continuation of pattern, even if we introduce non-biological elements to it, we would be continuing that pattern. And free will, that's impossible to define. I'm not convinced I have free will. Major decisions like starting a project, coming to work at Google, speaking at I/O. Did I really make that decision? What was I thinking? Just seem to happen on their own. I do actually think a lot, and I think I do have free will in deciding what to eat for lunch. So I think making eating choices is maybe the heart of free will. So I'll leave it at that.
Okay, that's very good. Thank you so much, Ray. This is just awesome. Thank you so much. Excellent. Your fans await.
Sweet. All right. Hello, everyone. My name is Chris McKillop. I'm the engineering manager for Android TV. I've got behind me here Leo Bagdasarian. He's the head UX designer for the Android TV stuff, and Andrew Gian, who runs the team responsible for the live TV integration in the platform. We're going to talk to you guys a little bit today about exactly why we bothered doing Android TV to begin with, and get into a little bit more detail than the demo we did during the keynote, and we'll have some more fun surprises at the end. So some facts and figures. Average American watches 30 hours of TV a week. That is a lot of eyeball time. 120 million smart TVs are shipped every year, and more than 5 billion hours are watched daily worldwide in front of their TV. This is a lot of time for people to be engaged in content from Google applications, from your applications. And these are computing devices now. These aren't just dumb panels picking up over-the-air signal. But there's no standard platform today. This is a huge problem for Google's app developers, for app developers around the world. You either need to do custom work for every single TV that ships, or fall back to just doing HTML. In-app purchasing and monetization, non-existent on a standard platform across TV, unlike in mobile. And TV looks a lot like the mobile space did in 2006, where you have all these manufacturers all building their own platform and all asking app developers to support them with no unified story. So Android to the rescue. Yay, established ecosystem thanks to you guys and thanks to the device manufacturers out there. 1 billion plus 30-day active users, 1 million plus apps on Play Store, 50 billion app downloads. It's incredible what you guys have helped us accomplish over the last few years. We have a huge support from the industry, both for SoCs and for networking, and across APIs and protocols. And more importantly, Play Store brings everything together so that you can do multi-device installs, in-app purchasing, and billing, so everyone can actually make money off this ecosystem. So what is an Android TV? It is just a new form factor for Android. We've announced several today at I/O, and so I wanted to welcome TV to the family with you guys. And so going forward, starting with L and going forward, TV is going to be supported right alongside phones, tablets, and wearables. There's not going to be, my goal internally at Google is actually that no one talks about Android TV in a year. That it's just assumed. Like, no one talks really about Android tablets and phones. Like, it's just Android. And that's what I'm trying to accomplish inside, and hopefully with you guys too. We've added a lot of great features for developers in L to make it really easy for you to bring your applications to the television. So I'm going to really quickly go through some of these, and then Leo's going to jump into UX. We've set really aggressive hardware specs for Android TV devices. We want to make sure that there's enough CPU and GPU in the devices that claim to be Android TVs to have really great performance for apps and games. Minimum of 1 gig of RAM and 8 gigs of flash, so there's lots of storage for apps. Wi-Fi and Ethernet for connectivity, so there'll always be fast pipes in. Bluetooth 4 and Bluetooth LE, which I think is going to be really important going forward for both accessories and for things like co-presence and things that could happen. Also wanted to ensure that there was a very high level of DRM. These are primarily media consumption devices. Android's always required Widevine level 2, which is fine for SD, which is OK on a phone. But we require Widevine level 1 on all TV devices. That's already studio approved in most of the world for HD content. We're not just targeting TV panels. I've been watching the press after the keynote today, and a lot of people are asking, hey, this is just for TVs. We don't understand. It's not. It's also for media streamers. I'm not going to mention brand names, but media streamers, set-top boxes. And when we say set-top boxes, we're talking about cable set-top boxes. So carriers like Comcast or Bouygues or SFR who are bringing premium content over their lines into your house. And also micro consoles. You're going to see a lot of boxes that come with a game controller over the course of the next year running Android TV. And we differentiate those from media streamers, both from the point of view that a micro console tends to have a higher CPU performance, as well as a higher price, and also not as approachable because of the game controller. We're standardizing input devices across all of Android TV, so there's a minimum set of controls. We have a virtual remote control app that you'll be able to get off the Play Store to interact with your developer devices if you request them online. We're also standardizing on game controller button mapping. We think one of the biggest problems we've had with adoption of game controllers on Android is the lack of a standard button mapping. It means that app developers had to worry about whether it was this controller or that game controller in their game. No more. So we're mapping all the popular ones to the standard for you in L, and we're publishing a spec for both game controller manufacturers and game developers so everyone can work together. So this will be across not just TV, but phones and tablets as well. So it'll be really, really powerful. We're also really pushing hard on all the hardware OEMs to have microphones in all their devices. We think that in the living room, no one wants to type on a keyboard. We have a keyboard. You notice we didn't show it during the demo. No one wants to type on a keyboard on their sofa. So being able to use your voice to really quickly get to the details of what you want is super powerful. We've done multimedia improvements. We've added new media components. We've built a TV input framework, and Andrew's going to go into great detail on that for you in a bit. We've switched to Chrome Web View and actually supports HTML5 video with DRM. So for folks that have an investment there, you'll be able to keep your playback. It's completely Google Cast supported. So all Android TV devices will also be Google Cast receivers. That means all existing Cast applications will just work. This is actually supported by the Cast team. This isn't a strange thing the Android team's doing on the side. The Cast team supports this. And in L, which isn't in the preview, but at L release, we're going to be adding APIs to allow your APKs to talk to each other through Cast. We'll call it Cast to Native or Cast to Apps. And that means that you'd actually be able to have first screen and second screen experiences at equal levels. Probably the meat of what we've added for TV in the L release is a new lean-back framework and launcher. And when we say lean-back, we're talking about, you're on your sofa and you're leaning back. And YouTube coined the phrase as a way to think about how people want to interact with TVs in the living room. And you're going to get a lot of details and background on that from Leo here in a sec. But we've added a new optimized home screen and system UI. We sort of merged them together. Sort of think of the notification shade, all apps, and your home screen all being in one place on TV. And we're requiring that all hardware manufacturers use our launcher. So there will be a consistency across these devices for developers. And developers can be guaranteed that certain behaviors are there. And we'll get into that with how the content recommendations work. We've also built a new set of fragments that you can use to really quickly take your existing APK and bring it to the television. I think this is the first time we've offered a standard element in the framework library that operates at such a high level. You can really just treat it almost like it's a data level API if you want to. It's going to be completely open source with the L Developer Preview. You can go in and change it around any way you want to, but you'll be able to really, really quickly get your app up and running. And for a bonus for all you Google TV developers out there, I don't know if there are any in the house, but if you want to support your Google TV v4 devices, our framework actually works on that. So there's millions of Google TV version 4 devices out there already installed, and this will give you a path forward. We've also been optimizing for TV Google's own internal APIs that you guys get through Play Services. So things like in-app purchase flow, Play Game Services, G+ sign-in, and we're going to be going through and updating all of them. So you can use the same APIs you use on phone and tablets and basically for free from Google get a TV optimized experience for your customers. Our studious head of design, Matias Duarte, who did a great job this morning in our keynote, always likes to say this when we start talking about TV. When your butt hits the sofa, you lose 20 IQ points. You don't want to think about it. You don't want to use a computer, right? You don't want your TV to be a computer. You want it to entertain you. And so on that, I'm going to bring up Leo to talk a little bit about designing for Android TV.
Thanks, Chris. Thanks, Chris. So people love TV. Not the demo yet, guys. When we began designing Android TV, we looked at the qualities that made TV so easy and approachable. We noticed a few qualities that made the content unique to TV. Like when you turn it on, you're instantly watching something. You're already in content. And how when it's playing, even when you're looking at a guide or a menu, it continues along, it continues the experience.
And how, at its core, it really is simple. Browsing is effortless. It's just channel up and channel down. And on top of that, movies and TV can be so emotional. They're so immersive and engaging. So when we really thought about bringing Android to TV, we wanted to do just that, bring Android to TV, and keep those content-centric, immersive qualities that make TV so great. So how are we going to do that? Well, we needed to design components optimized for browsing and watching content. One of the most critical aspects of design is how and where people interact with it. So with TV, that could be from 10 feet away, with food or drink in your hand, or with a baby, and even sometimes half asleep. For Android TV, we standardized a minimum button set to the 5-way directional pad, plus home and back. There's no menu button, and there's no pointer. So how does this affect app design? Well, of course, there's no touchscreen. So you don't have that random, quick access to different elements in your interface. So for most layouts, like on tablets and phone, you're going to have to kind of rethink how that kind of gets adapted to TV. With a D-pad, you have focus-based navigation. You move around by moving focus from one element to the other. So when you design your apps, you want to take advantage of those two axes of direction. Align your objects in rows and grids, so it's really intuitive to navigate inside your app. In the past, Android had basic support for focus-based navigation, but today we're announcing the Leanback support library. This is a collection of framework components that are optimized to build fast, fluid apps for TV. They're focused on content browsing with smooth animations and center-pinned scrolling. So your focus is always right there, center in view. But we went one step further. We built full application structure fragments, which can be used to create end-to-end apps. Let's take a look at the structure for a typical Android TV-based app. Most successful apps on TV are content consumption-centric, so they offer media like movies, music, TV, and pictures. Typically, a user enters, looks around, and finds something of interest, either by search or just browsing the hierarchy. Then, they get more detail like description or price, and ultimately finally play it. Included in Leanback are these full app structure fragments. As Chris mentioned, something that Android hasn't really done before. These can be used as is or customized to suit your app's needs. They're optimized for TV, overscan safe, with fast, fluid animations and support for immersive imagery. So bringing it all together. Using this navigation model and the new components of Leanback, we wanted to create an interface that was focused for entertainment. Thanks to all of you guys, there's a ton of great content in the Play Store that's just begging to be on the big screen. But we wanted to go beyond just the grid of apps. The TV and living room is about fun and entertainment. As you've seen from the keynote, there's a theme across Android to bring these contextually relevant notifications to different form factors. And that applies to TV as well. But these notifications they're not the same notifications you're used to. They come as content recommendations. We wanted a home screen that gave you quick access to like a blend of content from the sources you use most. One that encouraged the simple lean-back browsing and serendipitous discovery. And one that got to know you and made it easier to access your most used apps and games. And ultimately, one that felt immersive and engaging. And with that, let's go to the demos.
And your job is to tackle, dismantle. You want to see content, so we bring live TV and movies right to the forefront. If you're watching your content and you hit home like you would do on any Android device, we overlay that on top of the live content. These are new APIs that are coming in L to allow you to indicate that your app is, we call it gregarious. And so if your app is gregarious and willing to share its content with the launcher, it will show through. Otherwise, it's going to be hidden. you have the clicker? Oh. So when you first land in the home screen of an Android TV device, you're going to see these really rich content recommendations. So these are coming from apps on the system and are being ranked and sorted based on the user's usage of the device. So we rely on each of you to provide the right content based on how you know your users using your application. That's stuff we don't know. But we know based off the aggregate how people are using their device. And so we will sort and rank. I was showing pictures. I was showing Tommy Emmanuel to Dave Burke after the keynote. And so it's now YouTube's now recommending more Tommy Emmanuel for me. And I use YouTube a lot. So you'll see there's actually 2 of them on the screen here, because we know that I use YouTube a lot. This is my account. This is my personal device. So if you see something weird, it's just because I'm kind of weird. So the goal is that you come to this content recommendation stream, you see exactly what you want to watch, and you start watching it, and you're done. 1 click to play. What if you don't find something that you want? We decided to make sure that both search and all your applications are available. So there's a common pattern throughout the platform. You go up to search. So if you move up to the search affordance on the home screen, or you'll see when we go into the applications that search is also in the up position. So you can do search. So I'm going to use this to see if this works. It's always very dangerous to demo things with Wi-Fi, so forgive me. Let me see. Movie starring Tom Cruise. Thank you. So pretend this is my remote control, and I've got my virtual remote that has the microphone button. Hopefully, when you're using this on your TV, you're just using the remote control that's in your hand and picking it up and searching. So that search exists at the top of your home screen. You can go look for content that you're specifically interested in. Or you can look for actors or actresses. And of course, as Dave showed during the keynote, there's a ton of ways in which you can then pivot on both those actors and actresses using the Google's knowledge graph to find things. I'm not going to spend a lot of time on search because search is more of a Google feature and not necessarily a developer feature. I think it's much more interesting to start looking at what happens. How do you actually make content recommendations? How do you get into the apps row? Because you'll notice these apps look a little bit different than you're used to seeing apps on a launcher on an Android phone. We've standardized on a 16:9 poster for doing your application launchers. You'll see that we've worked with these first app developers and game developers to show and set the standard for how apps should work. Have the text of your name of your application in your icon. Have it big and bright and bold and on-brand coloring. And make sure that it has some movement and contrast. And that's true in both the games row and the apps row. So you want to know how you get in the apps row. So we're making a pretty strong statement with TV. We don't believe the TV should just be tablet apps on television. And so we actually are going to require developers to make a few changes to their application in order to show up in this new launching experience. So you have to add to your manifest the statement that I support lean-back. You don't have to use our framework, but you do have to declare that you support lean-back. And that way, the lean-back launcher knows that this application is going to work for the user that has a D-pad or a game controller. We don't want to offer up applications that immediately say, please touch here to continue on a TV where you can't touch anything. The same goes for games. If you want to be a game, you can declare yourself a game, and that's how we sort and separate the games in the app section. You might ask, why are we doing that? I use a lot of YouTube, a lot of Play Movies and TV. I've been watching TED and Showtime, and you'll see those are all in the left-hand position. They're the easiest for me to get to. I don't have to think so much. Again, 20 IQ points lost when you hit the sofa. So we make sure that the apps you use the most are at the left. Games and media consumption applications have very different access patterns. They have very different use models. When you play a game, you tend to play it a lot for a period of time, and then maybe you don't ever play it again. And that's not true with media consumption applications where you're going in and out of them based on what shows and what things you want to do. So we didn't want the games to get pushed away just because you were very rapidly and frequently entering a series of applications. So we promoted them to be their own top-level entity. So that's how you do that. So the recommendations come in through the standard Android notification system. We've added some new tags so that we can tell the difference between a notification that would show up in the notification shade on your phone and tablet and these notifications. We thought it was powerful to use the existing APIs and not try to invent something new when this would work just fine. Everyone is free to post this. It's a totally democratic system. And we watch how the user uses the device and sort and rank appropriately. We're recommending, I think, 5 to 10 notifications and content recommendations from different apps. Leo hates it when I do this, but I'm going to launch the Eat24 app for a second. They've done a really great job. And if it'll load the content from their app here, I should start seeing food recommendations like order a pizza in my content recommendation row, which is pretty great. You're sitting on the sofa watching a movie, you want to order a pizza. But it doesn't just need to be movies. The key to this, though, is we want these to be one-click access. We don't want people clicking on things on the content recommendation row and having to go through a big flow. So for example, like if I'm sitting here and I want to see Now You See Me, I can click on Now You See Me. I've been watching it previously, so it's going to resume, and it's going to kick right back into that movie. Our networking seems to be pretty slow in here.
And count
There we go.
1 to 10 out loud.
1, 2,
Okay,
3,
so-
4, 5.
Stop.
All right, so
Yes.
So I'm going to now dive in. Now, that movie is playing from Play Movies, as you can see from the script, from the content recommendation. I'm going to go into the top level of Play Movies now. Play Movies from Google is probably sort of a canonical example of a lean-back app using those lean-back components that Leo was talking about. This is the browse fragment, which we have set full screen for Play Movies because we're happy to use our own APIs directly. You can see that you can very quickly move through what we call the fast lane on the side, which will move you through all the different content on the right-hand side. You can move over to the left. You notice very smooth animation, transitions, fade-ins. These all come for free when you use the Lean-Back framework library. And then you can scroll through the same content again, but now with a little more details with ratings and the title of the show showing up on the cards, which didn't show up in this more compressed form. So if you go into one of these TV shows or movies, so let's go into Silver Linings Playbook. This is what we call the details fragment. It has a background, has the ability to put some text and some artwork, lets you play the trailer, buy it, and also then have additional browse rows built right in there. So reusing the same components that we had from the previous screen in the details view so that users have a grounding point where they can understand where they're coming from. Besides these sort of two browsing and details, if you have something like genres, like action adventure, you might want to throw up a whole bunch of content. So we actually have a grid view where you can just put tons and tons and tons of content. So if you try out PBS Kids, you'll see they use that as their only UI. Perfect for kids. Just all the cover shots for all the shows for kids, really brightly colored. They don't need lots of text on the screen. They know what show they want to watch. When they want to watch Calahoo, they want to go there. And so that works out really well. Let's see here. Now, in addition, we're going, not in the L preview, but coming with the full L release, we're going to have playback controls for you in the framework library as well. So Play Movies is using an early version of this. So if I hit the A button or the center, click on the thing, I bring up the transport controls. I can fast forward, I can rewind, I can play, I can pause. And you also get, just like in everywhere else in the system, you get browse rows. Let me see if I can actually get Woody Harrelson's face on the screen here. Come on. All right, well, I can't get his screen on the face. Play Movies does some neat things when you do that. But additionally, you'll get additional browse rows below the transport controls where you can get info cards, you can put up additional information, reviews. There's info cards on the actors in Play Movies that I'm trying to show you here. It's not being terribly cooperative. Oh, well. So those transport controls are going to be coming with the L release. So I want to go through some different examples now. So if that's the canonical form of all the different screens that we give you for free in Leanback, what I'd like to show you now is YouTube. So I don't know if any of you used YouTube on a TV before. YouTube has a pretty standard application that they put on smart TVs. And they worked with us to bring you the YouTube experience into using the Leanback framework. Now, they really liked having the fast lane down the side for going through all the different playlists I subscribe to and all the different content. But they didn't want it to just be browse rows. They wanted it to be a grid. So they made that modification using standard framework components so that they could have a grid of content because they have so much content in YouTube. Simple rows wasn't enough for them. So you can very quickly move through the content. It still feels like a Leanback app. It still feels like an Android TV experience, but they are using slightly modified versions of the framework. So the TuneIn Radio guys have supported Google TV for years. And so we reached out to them when we were getting ready to do this launch. And they said, well, yeah, we'll bring our Google TV app over and it'll be fine. And then they saw all the apps we were building. They said, well, we want our app to look like that. And so a week before I/O, they said, we're going to rewrite it all. And so they did. And so they wrote this app that uses the framework components in 1 week. It looks just like Play Movies, which is what you'd expect because they haven't had a chance to go in and make big changes to the app. But it just shows you that they were able to bring a fluid, fast-operating application to Android TV, one developer, I think, in like about a week. It'll be on Play Store in the Preview Play Store. Pretty impressive that they were able to pull that off. Now, the TED guys have sort of a very distinct set of design guidelines that they want to use for their applications. So although they're using the same Leanback framework that everyone else is using, they have a totally and radical different look and feel. So, but this is still using the same browse-based rows, but they've changed the cards and they've changed the card-to-card animation, which is all possible. They've clipped where the rows are on the screen so that they can have the full bleed art that you see as you go through the different movies. So it's completely compliant with the design guidelines. It's using the framework, but it looks like a TED experience. This is one of the big goals we had for this was to have that kind of flexibility for app developers to both quickly get on the platform and get Adopt TV, while also have the ability to make those sort of customized brand-on changes. And now, the last one I'm going to show you is Showtime. Now, the folks at Showtime have a very strong design for their application on TV. This is completely custom widgetry. So they don't use any piece of Leanback. But the Showtime guys understand Living Room. And so it's OK. They've written an Android application that uses low-level Android framework components to do focus management. But they're not using the Leanback. But that's OK, because they're fully compliant with the left-to-right navigation, the up-down browse paradigms, and everything's usable with a D-pad. So this sort of shows you just sort of the levels and the degrees to which you can make changes. So on that note, I'm going to end my part of the demo and switch back over to slides and let Andrew come and talk a little bit about the live TV integration on the Android framework. Thank you, everyone.
Thanks, Chris. So with the Leanback framework, we expect you guys can build apps quickly. And then this app will mostly serve audio-video content. And then we believe it could fulfill all the user's experience. But if you think about it, actually, there is something big missing. So if you think about TV device, both TV set and set-top boxes from operators, and even streamer boxes, a lot of people recently believe that TV experience, video content watching experience in the living room will move from broadcast TV to online streaming. However, the data shows that still in many parts of the world, majority of the time user spends on watching video content is live TV. So we wanted to build a framework to support proper live TV integration to build a device like this. And as we mentioned in the previous slide earlier, there are still hundreds of millions of TVs and tens of billions of set-top boxes are being produced in the world every year. And when if we want to claim Android to be an operating system to build a TV and set-top box, we thought we need to have a framework to support these kind of devices. So when it comes to making a TV or set-top box, first problem every device maker faces is that there are a lot of different TV standards. Like, it's not that much fragmented, but this is one layer of it. It's only digital broadcasting standard. But if you look into more sub-standard, there are many more. So it's very complicated. And then each device maker chooses their own solution to fulfill the requirement for each market. And it only works for that device types. So we thought that in order to make Android as an operating system to support these device makers, we thought we had to have some kind of a good framework. And then, in addition to TV standard, if you look at the TV device especially, there are a lot of different physical input ports, HDMI component, AV port, and built-in tuner. So what does that mean is people usually hook up a lot of devices to TV. And of course, still, for example, in US, more than 80% of the people living in US watches TV from pay TV operator set-top box. What does that mean? Is that if you look at your living room today, there are a lot of remote controllers lying around, and whenever you play game or play Blu-ray disc or watch TV, or depends on your activity, you have to pick up the right remote control, and then a lot of devices are competing against your time for each HDMI input. So this is quite frustrating. So we've been thinking about a solution, how we can fix this. But we cannot fix it ourselves alone. So we need some support from the developers. So let's take a look at what we built so that we can give you an idea of what we expect as a whole ecosystem, including ourselves and developers, can do to solve this problem. So during the keynote today, should I press something? It's stuck. Oh.
Yeah, tell them to switch to the demo.
Could you? Oh, okay. So there was not demo. So there was a screenshot somehow. So sorry, I was too vivid, so I was confused. So you can see the icon called TV, and if you click it, you can watch TV. In the sandbox, if you visit the sandbox today, you can actually watch real live TV over the air upstairs. But here, for keynote and demo, we are using mock-up demo. Basically, we are using some local file to demonstrate multiple channels. So as you can see, you have a standard channel banner, shows up title of the program and timing and things like that. And then if you bring on a menu, these are channels user has been watching recently, and it's being automatically ordered by the frequency and then ranking. We thought user may want to go back to the channel. And then these are the menus. This is a preview version. We just spent like few weeks to put together this UI, so it's going to be much better in the future. But for now, we have some essential options. And one thing I want to show you is the TV input menu. So the concept of a TV input is very important to us. We wanted to come up with a single application to watch every single live channel, but there are multiple ways to get live TV sources. So we define a concept called TV input. TV input represents a method to provide list of channels. So in this case, we actually called out unified TV input, but in the future, there will be no unified input. TV app itself will run in a unified input mode all the time, but just for now, they're separate. And we have 3 different TV input sources. If we click each one of them will have their own channels, fake channels. So the first one has 2 channels, and then let's go back. And then second one, if I choose the second one, this is to demonstrate HLS-based stream. This is very common test video most streaming content developer knows about. And then here we just have 3 different fake channels. So this shows you each input can have a different channel. So if I go back to our demo TV input, we can see 4 channels, which look nice because we fake up. It should be nice. So concept is when you switch different TV input, you can see different channels. But in ideal world, user shouldn't have to change the input from HDMI 1 to HDMI 2 or something. it shouldn't happen, or built-in tuner. So the idea is we wanted to unify all of that. So this mode, unified input, demonstrates how we merge all the channels. So if I go back to channel listing, you can see every single channel from every single input. That's the concept we built. And this should be the basis to do anything on top of it around live TV. That's why I wanted to show. Let's go back to slide to talk about it a little more. Slide, please. Okay. So this is the UI use, so I thought it was live, but it's not. So basically, there are multiple ways the live TV source can be delivered to user. First of all, many parts of the world still over-the-air broadcast is very popular. You have antenna or cable, just cable to get the antenna feed to your living room and hook up and then scan and watch. Second is paying some money to pay TV operator, and they deliver you a set-top box, and set-top box actually gets you a live TV feed. Up until recently, cable operator or satellite was popular, but these days, IPTV operators are getting more popular. So this second type. Third type is just purely from IP. And in this case, there could be a pay TV operator which uses IP, it's IPTV operator, or some online sources. But we wanted to be able to unify all of this if user has a multiple access. Let's say in some countries like Luxembourg, it's crazy country where you have access to 4 different countries' TV feed, and then 3 different type of TV standard and online sources. And people in Europe move a lot. So Germany people live in France and they want to watch the Germany channel. And English people live in Sweden and want to watch the English channel. So it's all mixed. So especially in Europe and even in some other part of the world, people has a demand to watch live TV channel from different worlds. How we can solve that? So let's say we unify, we build a framework. So some application as a plugin to live TV app can support the live TV feed. Then we just unify it into a single lineup. And then we can filter them by category or quality or by user's preference on top of it. So the reason why I'm talking to you today is we cannot build this unified channel ourselves alone. So there are a few use cases we can get some help from developers. First use case is, let's say you're just getting the TV signal from pay TV operator set-top box, like most people in America. Then how can we unify that? How can we use a single remote control to watch live TV and at the same time enjoy a bunch of online streaming content and play game? So in this case, we expect some developers to write a module. And this category, we just categorize it as a virtual TV input. It is a APK, which includes TV input service. You will learn the detail about it tomorrow once the SDK is published. So virtual input can talk to set-top box if they understand how to talk to. They're usually, recently many pay TV operators are publishing the protocol to talk to the set-top box or cloud API to check the lineup of the subscriber and fetch EPG data, and then even send a command to tune. So this virtual input module can translate the command from the single system live TV app to tune, and then get that command, translate to proprietary command the set-top box understand, and actual AV data can come from set-top box through HDMI port to TV device. So then, from user's point of view, user is using TV app you just saw to watch TV from set-top box and change the channel to Android TV, but actual change channel action will happen on the set-top box. That's what we call two-way pairing, two-way connection. So that is actually possible today with many pay TV operator set-top box, and we do have a close partner, some third-party developer partners who are working on a few versions of this, and we hope some people in the room or in the world to build these kind of things to bring seamless experience. Second case is, as you can see in the sandbox today, the device we have here doesn't have any tuner. but it can actually watch live TV. How can it be possible? Because there's an external device which converts broadcast feed from antenna or cable provider into IP feed. So in this case, IP input device can get the AV data from the device, which we call as a place shifting device. Shifting place means that, let's say you have an antenna feed coming down the corner of the house, and then you place it here, place it there, and then once it converted to IP, anywhere in your house where your Wi-Fi connection can be reached, you can get the signal. So that's why we call place shifting. So there are many types of devices like this, but today in Sandbox, we are using the device called HT Home Run, made by a company named Silicon Dust in Livermore. So it was very small and easy to use device we are using. So that device has its own command set for us to fetch EPG data and also send the command to tune. And then we can publish the EPG data to the common database in the Android TV device. Then live TV app can render channels and watch TV. Lastly, in case where live TV signal is delivered via IP, one can write a TV input module that gets the feed via IP, push the AV data via IP, and send a command over IP. So there are two cases of IP inputs. One is multicast IP input on the managed network. For example, IPTV operator has their own managed high-quality network. So this input can actually join multicast network and stream TV. In the other case is that if any content provider or broadcaster has a server somewhere in internet, provides adaptive streaming-based live TV, then this input can go fetch it. Basically, it's a streaming, but from user's perspective, it's a live TV. So that is actually quite common by many operators. Let's say you are a Time Warner customer or some of the pay TV operators customer in some part of the world. Then as a subscriber, you get access to their IP feed so that you can watch TV on your tablet or phone. The same type of sources can be used to power live TV on Android TV. So as a result, we imagine one day, no matter where you are getting live TV sources, we hope users to enjoy all the content, including live TV and streaming content and games using single remote control and game controller. That's our hope. So there's more. So probably there are many people who see me multiple times. I've been pushing the Android framework to enhance the AV pipeline for many years. And now we are really getting close with L release. We are asking developers to build the apps to deliver content, especially video and audio. The problem is if Android platform itself is not capable of supporting your streaming protocol or closed caption or high-quality video playback, even if we build a lean-back framework, it's actually not easy to write apps. So what we've been working on is enhancing the video framework. So first of all, in terms of supporting streaming protocol, we have a separate session going on either today or tomorrow about XOPlayer. XOPlayer is open sourced, will be open sourced video player, uses low-level primitives such as video crypto, video DRM, and video codec. And it's a Java implementation of video player, and it gives you MPEG Dash and smooth streaming protocol implementation by default. And since it's open sourced, you can take the source code and then implement your own custom streaming protocol if you have, so that we will not be the blocking factor for you to support your content in your backend, so that you can write an app that stream your content. And on top of that, there has been a lot of requests to support more various type of subtitles. So in L release, at least we are adding TTML and CA608, and especially CA608 was high demand request from many content providers because especially TV shows being captured from broadcast and then delivered as a streaming video, their closed caption source is encoded in CA608 format. So unless we support that, those content cannot be supported. And now we already support WebVTT since KitKat. So we have 3 formats. Maybe there are some other formats too, but these are what we can support by L. And when user play content on phone versus on the TV device, TV screen is big. So if there's any glitch in terms of audio-video sync or video rendering, user can notice easily. So the bar for video playback quality is very high on TV. So we spend a lot of energy on making audio-video playback quality to be TV quality by using TV Associates feature to turn on audio and video. And we starting to support VP9 and HEVC codec to support 4K content. And HC3 obviously to support ATSC content. And as Chris mentioned, we support Wi-Fi level 1 and ProReady. Thanks. Right on top.
Thank you, Andrew.
So during the keynote this morning and also in the sandbox, if you've seen it, and up here, right here, we've been demoing all this on real hardware. And we call that hardware ADT1. So some old guy once said, which came first, the chicken or the egg? This is an important statement when you're building a new platform or adding a new device type to an existing platform. App developers don't want to support you if you don't have a piece of hardware for them to develop their apps against. And hardware manufacturers don't want to support your new platform unless you show them running it on another piece of hardware. And so we were the only ones that could fix this. So what we did was build ADT1. This is a media streaming micro console, choose your acronym that you want to have, but we built it for developers. We built it originally for inside of Google. This chicken and egg problem exists with everybody. Everyone has too busy schedules and doesn't have time and doesn't necessarily believe that what you're building is real unless you give them something to play with. So what we've decided to do is take that box, which is a Tegra 4 CPU, 2 gigs of RAM, 16 gigs of flash, 2x2 MIMO Wi-Fi, HDMI. It's running L Developer Preview, and it's fully unlocked. It comes with a developer cable, so that you can reflash it and do whatever you want. It's essentially the same level of openness as a Nexus device. And so everyone here at the session today is going to get one of them. So everyone watching the live stream, starting tomorrow, you're going to be able to go online and request one. We have a small number that we're going to give to existing Android developers. Please go online to the URL there. It won't be live till tomorrow, and request your device, and we'll get those out to you. So this should let everyone here in the room experience what we've been showing you. Start bringing your apps over to Android TV and really sort of see what's next for Android. There's going to be vouchers. You'll get the device tomorrow with all the other hardware. There's vouchers that'll be at the doors. Make sure you get your voucher on the way out. And don't rush. There's lots for everybody, okay? So just get your voucher. You'll be able to pick it up tomorrow downstairs in registration. It won't be a problem at all. So I want to thank everyone for coming to the presentation today. We'll have all the documentation, screenshots, example code, GitHub projects up online tomorrow for you to get moving. So enjoy and thank you.
Think of a network operation that would not update the UI. The types of jobs I'm talking about are also self-contained. One way to think of it is that we're interested in execution logic that can be easily refactored. Another way to think about it is that there's some bundle of parameters that you need to know to run your task. The name of your user, the list of rows in your database that are dirty, or the list of contacts that the user has requested be uploaded. So why create a new API? You might wonder at our rationale when clearly these things have been possible for as long as Android has been around. Well, not quite. Take network calls as an example. These are a strong candidate for the kinds of work we're interested in. Apps usually do them ASAP to kind of get them out of the way. This leads to unnecessary radio wake-ups where everyone is doing their own thing haphazardly. To tell you some more, let's take a look at how we might write code to periodically upload data, but without the job scheduler. There are about roughly two ways you could have done this. You could use a handler and post a delayed message if the period was small enough. But what happens if the user kills their app, or if the system does? At this point, you decide the alarm manager is for you because at least you'll be started when the alarm goes off. The problem is now that if the phone turns off, your alarm is gone. So you're stuck doing your own persistence. Then what if an execution time, the network wasn't available? You'd need to handle this and try again later. You'd have to register a broadcast receiver so you'd know when connectivity came back. I guess you could try writing a sync adapter, which kind of solves a bunch of these issues for you, and it's an excellent piece of code, but it's not intended to be used for scheduling. Regardless of route, it would be a mess and difficult to get right. So we've decided to get it wrong for you. We've taken pre-existing functionality, wired it together with new functionality, and are giving it to you in a nice palatable package. We've introduced the concept of idle mode, a window of time for which the system has determined the phone is unused and is not likely to be turned on soon. For example, having a job run while the device is idle and also charging is likely to happen at night when the user is sleeping with the phone plugged in next to them. The second thing we've done is integrated closely with new system APIs that inform clients when the network is active. This means that the handshake with the carrier has already happened. So when we batch your app's network calls to follow on shortly after, it'll circumvent the battery cost of you doing this handshake independently. Less pesky battery blaming and battery stats for you, and more battery for our users. So let's take a look at how to use this functionality. Here we'll see the sorts of work you might like to express. Run this when the phone is plugged in. Run this whenever an unmetered network becomes available, but make sure I run within the hour. Wait at least 10 minutes and then run this the next time the device is idle. Every 15 minutes, whenever a network is available, let me know so I can do some small health check. These 4 use cases, there are a number of constraints, and you can specify as many or as few of them as you want. The scheduler will only run a job that has all of its criteria satisfied, the one exception being when you set a deadline. When this deadline expires, it'll override the existing constraints. Let's take a look at how we do this practically. For this job, we're setting the deadline of an hour. But what will happen if the phone is in airplane mode after the hour has expired? Well, we'll talk about failure retry in the next and last section. For now, let's look at some other interesting things. My job service is the endpoint you provide. Here, you're identifying it so that the system will know where your job should land. Wi-Fi upload ID is this handle on your job to differentiate it from others as you schedule. So arbitrary integer that you pick yourself. You take this job info object and you pass it into the system in the normal way, and voila. But where does my logic go? Okay, so you extend a service provided by the framework. The framework service handles all of this.